Have you ever felt that organic chemistry is the villain and its most lethal and dangerous weapon is this chapter of aldehydes and ketones? Because yes, carbonyl compounds is the heart of organic chemistry, which basically controls everything, right from those life-saving drugs to the flavoring agent in your favorite food and to those tricky questions of JEE. So hello my dear JEE aspirants, and I am here with this very important chapter of aldehydes, ketones and carboxylic acids, and I have personally curated these handwritten notes in such a way that we'll be discussing whole of the mechanism, as a result of which all the theory which you used to mug up initially will just be a byproduct and will be a conceptual application. But you have to promise that you have to finish this video till the end, take these lecture notes which you can obviously download for free, and along with that the selected problems for your JEE Mains April attempt. So where to download all these stuff from for free? Just go to the link in the description section where you will be directed to the wonderful world of PW, which is also helping thousands of students like you to excel in their competitive journey. Now, you can also scan this QR code and follow us at our PWJ English WhatsApp channel. So let us start this carbonyl compounds. So to begin with, let us do the classification of carbonyl compound. Now, what is a carbonyl group? This C double bonded oxygen is known as a carbonyl group, and this sp2 hybridized carbon will further have two valencies. So if one of the valency is hydrogen and obviously the other valency is any hydrogen or any carbon containing group, then it is known as an aldehyde. If both the valencies are carbon containing group, then it is called a ketone. If one valency is substituted by OH, the hydroxy group, the alcoholic group, but if carbonyl group contains an alcohol, then this functional group becomes very reactive and it is known as the most famous functional group called carboxylic acid. Why I'm saying famous? Because this carboxylic acid also has some derivatives. So what are these derivatives of carboxylic acid? If you replace that OH with an halogen, it becomes an acid halide. If you replace that OH with a nitrogen, it becomes acidamide. If you replace that OH with OR as an alkoxide, as an alkoxy group, so that becomes an ester. And if you take one of this acid, so one acid will be forced to give OH in presence of a dehydrating agent, and the other molecule of the similar type will release H, so they will undergo dehydration and they will result in the formation of the last derivative, which is called acid anhydride. Now, in order to practice their IUPAC and naming, let us go and practice these NCERT examples. So to begin with, I'm explaining all the IUPAC logic that we know, but if some student is starting from zero, still you can understand this with this only. But if you need a very detailed analysis, then I have done this IUPAC and isomerism separately in GOC1, so please kindly watch that, but that will be taking around 1.5 hours more. And if you are just learning this for your JEE Mains and boards, and if you know something around IUPAC, then this much is obviously more than sufficient for you. So how do you name an organic compound? Sir, organic compound is named in 5 columns. The third column represents the word root, which represents the maximum number of carbon atom that is present. Now, how to select main chain? Selection of main chain rule says that you have to select that carbon which is directly connected to a functional group. And so that means the first priority we give is to the functional group. So can you see a functional group? Yes, sir, we can see a functional group. The functional group is the C double bonded O carbonyl group, because it is connected with an H. That means it is definitely an aldehyde. Now, so we definitely know this is an aldehyde. So this functional group is connected with which carbon? Sir, it is connected with the ring, with the cyclic chain. So that cyclic chain becomes the first carbon. And post that, because we give minimum number to functional group only, so that becomes our first carbon. Now, after that, numbering says you give minimum number to functional group. Post that, multiple bond, it does not have any multiple bond. Post that, lowest location, as in all the branches should be given minimum number. So if I give 2 like this, then 3, then 4, then 5, then 6. So this has enabled me to select the main chain and number the main chain. Now after that, how to name the organic compound? Column 1 says you name the prefixes of all the branch. I hope you know it contains only one branch, that is the methyl group connected to the third carbon. So column 1, the secondary prefix will be 3-methyl. That's it. It contains only one branch. Column 2 signifies that whether your main chain is cyclic, then use a word called cyclo. Column 2 gone. Column 3 represents the main chain. So how many carbons are present in the main chain? 6. So hex. Column 4 represents its primary suffix, that is the level of saturation and unsaturation. Because the 6 carbon chain is saturated, so I'll write an N. And last, the 5th column, we talk of the secondary suffix, that is the functional group that is there. We have to know its suffix. So what is the suffix for aldehyde, where we have to name this carbon also? So this carbon bonded with H and with this double bond O. The suffix for aldehyde group with carbon is called carbaldehyde. So its suffix is carbaldehyde. What is generally the suffix which we use? We generally only name the double bonded oxygen. We do not name the carbon. We take the carbon in the main chain. But whenever a functional group that is containing carbon is directly connected to a ring, then its other suffix is used. What is the other suffix? The suffix in which you name the suffix, you name the functional group as well, and you name the functional group along with that carbon, because this carbon is not included in the main chain. The main chain we have taken just this 6 carbon. So in that case, the other suffix will be used, which is carbaldehyde. So this will be your name, and this is how we have revised the IUPAC of all the organic compounds. Now talking about this example, so obviously I can see it's a 3 carbon chain. So obviously, because this carbon has to be a tetrahedral carbon, so there will be hydrogen. Even if we draw it or we do not draw it, we know carbon is tetravalent, so there has to be one hydrogen over there. Okay, now selection of main chain. So obviously this is the functional group, so this carbon becomes the first carbon and will be present in the main chain also. After that, so multiple bonds, so this becomes 2, this becomes 3, so I have a 3 carbon chain. Now because it is not having branch, so column 1 does not exist. Because main chain is not cyclic, so column 2 does not exist. What about column 3? Word root. How many carbons you have in the main chain? 3, so it becomes prop. Because main chain is unsaturated, and unsaturation is where? Between 2 and 3rd carbon, so take the lower number, that means prop 2-ene. And where is the functional group? Sir, at first carbon. Now just make this thing sure that now you have to name what? Sir, now we just have to give suffix to this double bonded O, which is definitely an aldehyde. But this carbon we have already named in the main chain, because we have taken 3 carbons in the main chain, so this carbon is already included in the main chain. That's why what is the general, what 90% of the time what suffix do you use? Which we are using right now. So suffix for aldehyde is AL. And because A is a vowel, so this E will be cancelled. So one you can even write or you cannot write, so that in paper you always have an habit of writing name like this. But if at all in paper, how can the examiner can ask you? It is to in al. They can even eliminate this E. They can even not show this 1, because if no number is given, then definitely the numbering is 1 only. So examiner can give you the name like this as well, but you should know that how that name has been constructed. So coming to the other examples, let us explore these other examples. So obviously, what is the simplest aldehyde? Sir, 1 carbon aldehyde. So if I have a 1 carbon aldehyde, it is methane-1-ul or simply methanol. But industrially, some compounds are so important that their general name is so much loved by JEE also, by even class 12 board examination also. And I guess you know this from class 10th only, that 1 carbon aldehyde is generally named as a formaldehyde. if I have a 2-carbon aldehyde, its IUPAC name will be ethanol and its general name will be acetaldehyde. Now, 2-methyl propanol, as in if I have 3 carbons aldehyde, but at second carbon I am having a methyl group. So sir, with hydrocarbon in the previous chapter we know this, that there is a general name called iso group. What is that? I have first carbon, second carbon and a methyl branch. This photo, I hope you remember, is known as iso photo. So generally isophoto is formed by how many carbon? 3. But if to that free valency you add one more carbon, it becomes isobutyl group, and to that 4th carbon if you make it an aldehyde, so it becomes an isobutyraldehyde. That's the general name. So the general name will be isobutyraldehyde, and obviously its IUPAC name will be 2-methyl propanol. General naming for carbonyl compounds are not important. They are very, very important. I'm not saying, although many times even the direct question comes from the general naming, but most of the time whatever reaction JEE, even class 12 board ask, they use their general name. So you should at least know their general name by heart. So even I have not taken some irrelevant examples, some advanced level examples. These all are the examples from NCERT, and I have deliberately taken those NCERT examples to make a note of them, that you should remember them all. Very important. Now, obviously coming this example we have done. Now one more thing, sir, general name is also written over here. What is this? So obviously we know that if you have a functional group, then the carbon next to functional group is generally also numbered as alpha carbon. For example, if what is our functional group over here? This CHO. So this functional group is connected with which carbon? So this functional group is connected with this carbon. So this carbon becomes your alpha carbon. And post that, if you're generally forced to name it, and in a general sense to number it, then this carbon can be termed as beta carbon and this carbon can be termed as gamma carbon. So some people can generally also name it as gamma methyl and whatever name now you know. Like for example over here, gamma methyl and whatever name that you know. Similarly, coming to this option, so obviously we can obviously see from here only, this is carbon number 1 because it is connected with the functional group aldehyde. This is carbon number 2, this becomes carbon number 3, but with second carbon now I have a branch of OCH3. What is branch OCH3 called? So it is called methoxy group. So its IUPAC name will be 2-methoxy propanol. And obviously it is at the next carbon because this is the functional group. So this carbon becomes the next carbon, that is alpha carbon. So generally it can also be written as alpha methoxy. Now 3-carbon aldehyde is generally termed as propionaldehyde. Very important. Now, what is, sir, so 5-carbon aldehyde is also generally named, yes, although not very famous, but for good questions you should know this, that pentanol, this pentanol is generally named as valeraldehyde. You name these, you take name of these compounds few times, then they will be very much clear to you. Now, next is a very famous monomer that is industrially used as a polymer, this compound which is generally known as acrolein. Now what is it? Sir, first carbon, second carbon, third carbon, that means that it's a 3-carbon aldehyde but with an unsaturation. Obviously we have already named this compound in the previous slide. So this is known as acrolein, and this acrolein is nothing but this compound that we have just named, prop-2-ene-1-ul, or just prop-2-enol. Now, sir, talking about some more examples. So, sir, aromatic aldehydes, obviously if benzene ring has a CHO, then the name can be benzene carbaldehyde, or generally it is named as benzaldehyde. It is, although here benzaldehyde is not, I mean, I'm just giving you that name. We know that already, that if I have a benzene ring that is directly connected with CHO, it is called benzaldehyde. Yes, it's a general name, but these general name of aromatic compounds are even so very regularly used that even IUPAC accept these general names. So this is benzaldehyde, and if I have benzaldehyde at ortho position to each other, then what should be the IUPAC name? Benzene 1,2 dicarbonaldehyde. But sir, we know that for them obviously there will be some general name. So the famous general name is phthalaldehyde. Phthela, you know that phthela, so you can remember it like this, that you are holding it like this, so it is phthela. Corresponding acid is called phthalic acid, so this is called phthalaldehyde. Now obviously this is quite, now we already know this is benzaldehyde, so this is from aldehyde, it is meta position 1,3, so it becomes meta bromobenzaldehyde. IUPAC name will be 3-bromobenzaldehyde. Sir, what about ketones? What can you say about the smallest ketone? Sir, the smallest ketone, for a ketone, carbonyl group should have carbon on both the side. So I guess it is quite clear to you, it is quite evident to you that what will be the smallest ketone. Sir, in order to have a ketone, this carbonyl group should have alkyl group over here also or here also. So this is the smallest possible ketone. So smallest possible ketone is prop-ane-2-one, and even if for this ketone specifically you do not put 2 over there, like for example if somebody has written prop-ane-one, and obviously this E will be cancelled because I have a vowel, but you make this thing, you please note this thing that I am not putting 2 over here. Actually its name will be propane-2-one. But sir, you said that if you write 1 or you do not write 1, we can understand that, but here you must have written 2. No, for this propanone, even if you do not write 2, it is good. Why? If somebody is thinking, sir, not written number, so it will be 1. If you are putting at the first carbon this double bond O, then it becomes an aldehyde. So for this propanone, for the ketones, if you do not put the number, then still for them you have to think in your head, because in order to make them ketone I need alkyl group on both the sides. So this acetone can even be written as propanone simply without the number shown of the functional group. Similarly, now if some general names, if the carbonyl group at the one position, one free valency, it is having a phenyl group, at the other free valency it is having methyl group, it is also a very famous general name, even accepted by NCERT. This is known as acetophenone. In order to learn this, what is this? So let's say this is phenol, and if phenol and acetic acid forms a ketone, it is known as, I mean it's just a way to remember it, it is known as phenol ketone formed by acetic acid and phenol, so acetophenone. Now if I have a 3 carbon over here, it is generally known as propiophenone. If I have benzene ring on both the sides, it is generally named as benzophenone. These are very important general names of ketones. Now moving back to ketones, okay, these examples we have skipped, so let us now practice them. So this is carbon number 1, carbon number 2, carbon number 3, 4, 5, because functional group should be given minimum number. So IUPAC name will be 5 carbons, so pent-ane-2-one. Now here we have to specify 2. Why? Because third carbon can also have a ketone. Although this fourth carbon have a ketone, if this fourth will have a ketone, then I'll definitely number it from this side only, so it will be just propane-2-one. But here writing 2 is mandatory, because even this 2 can have this ketone, even this 3 can have this ketone. I hope it is clear. Now obviously this compound, let us draw the structure. So there are CH3, 2 CH3, so 1 CH3, then I have a C and another CH3. So there are 2 CH3 connected with a CH, so that this becomes CH, followed by I have a double bonded O, and post that I again have that CH, 1 CH3 upside, 1 CH3 downside. So how to draw these condensed formula? Always think of the tetravalency of carbon. If you think of the tetravalency, you are definitely going to get the structure right. So this is the structure. How to name it, sir? Main chain is already, I mean, quite visible, because it will be having the functional group and the maximum number of carbon chain. And in order to number it, I'll number it from any side. Let me take another pen. Let me take this one. So this is 1, 2, 3, 4, 5. So it is a 5 carbon chain with second carbon and fourth carbon having the methyl group. So its IUPAC name will be 2,4 dimethyl pentane 3-on, because third carbon is having the functional group ketone, so 3-on. But why I am discussing this question? Because general names are very important. Now if you note this ketone is having both the alkyl groups similar, and if you circle this alkyl group, then you can quite easily see that, sir, that it is isopropyl group. So this ketone is having isopropyl group on both the sides, so it can also be generally named as diisopropyl ketone. Such general names are very, very important. That's why I'm deliberately discussing this now. Coming to this, obviously it's a ketone, so this will become number 1. This is 2, so this is 2-methyl cyclohexane 1-on. General name will be alpha methyl, because this position can also be termed as alpha position, the carbon next to the functional group. Now what about this one, sir? Obviously functional group will be near from here, so I'll be numbering from this side 1, 2, 3, 4 and a 5th carbon, but this 4th carbon will have a CH3 group also, because there are 2 CH3. So one CH3 will act as a 5th carbon and one CH3 will act as a methyl branch. So its name will be 4-methyl, the branch, pent 3-ene, because multiple bond is between 3-4 carbons, so smaller number is 3, so 3-ene and then 2-on. What about the general name? Sir, these examples are very common, so I am not saying IUPAC is very easy. Then sir, why you are discussing all them? Because I want you to at least hear their general name once. Yes, for good students you will read them and you will practice them back at home also, but at least my job is to bring these names to your ear, because they are very, very important general names. So this is known as mesitile oxide. This is known as mesitile oxide. In 2024, there was a question with, if you just know this mesitile oxide, IUPAC name was asked. So I am deliberately taking this NCERT examples. Now, obviously for aldehydes, I know 2-carbon aldehyde is generally known as acetaldehyde. This is benzaldehyde. I have an drawn. And we now know the general positioning. So this is alpha carbon, this is beta carbon, this is gamma carbon. So this can also be generally termed as beta whatever. For example, I have bromine over here, so beta bromo, and then 4-carbon aldehyde is generally known as butyraldehyde. Now, as in starting of the chapter, I told you that these carbonyl controls everything. Vanilla ice cream that you have, what is that vanilla essence coming from? Naturally it is coming from an aldehyde. This aldehyde is generally known as vanillin, which is present in your vanilla ice cream. And this vanillin, what is it? It is aldehyde, and then at the 3rd and 4th carbon, at 4th carbon you have a hydroxy group, and at 3rd carbon you have a methoxy group. So OH, alcohol, OR, ether. But what OR? Methoxy. Very important name, general name. This is called vanillin. Now, this is salicylaldehyde. We have already seen this in the chapter of phenols, alcohol, phenol and ether. And salicylaldehyde is this basically, you have seen DDLJ Shah Rukh Khan picture. Now the flower, the yellow color ka khet, that yellow flowers, the smell that the flowers has is because of this salicylaldehyde. Now this cinnamaldehyde, you must have gone to your own kitchen. The dalchini is nothing but dalchini is cinnamaldehyde. So what is the cinnamaldehyde? When this benzene has a conjugated alkene, and to this conjugated alkene, if you connect a aldehyde, then it becomes your cinnamaldehyde. Now these are very important. Obviously, I'm saying these are very important. These are very important. Moving to another example, you will see such examples even asked in JEE question directly. So please make note of them. Obviously, you can download these notes, but after downloading, please read them at least once so that you can recall these general names whenever required. Now, so these are some examples which I have. So let us see them at least once. So let us name them. They are IUPAC name. This is carbon 1, 2. So this is just simple ethanol. What about this? Carbon number 1, 2, 3, 4, 5, 6, 7. So 3rd and 4th carbon are having branches. Fourth carbon branch is starting from a B, so I'll write it first. So that means 4 bromo, 3 methyl, 7 carbon, so hept, saturated, so in 1 ul. What about this one? It is a ketone, 1 2 3, so it will be 3 methyl cyclopentane, 1 one, because obviously you have 5 carbon main chain. What about this one? So now I'll not say ul. Why? Because ring is directly connected with an aldehyde. So I'll use the other suffix, which is not ul, which is carbaldehyde. So cyclohexane, 1 carbaldehyde, 1, even if you do not write. So it goes, it is good. I mean, you make an habit of writing 1, but if question is asking you that this is the compound, then you can think that it has not written 1. What about this one? Carbon number 1. Okay, I'm sorry. Carbon number 1, 2, 3, 4, 5. So again, it is a 5 carbon aldehyde, but with unsaturation in 2, 3. So pen 2 in 1 ul. Obviously quite clear to us now. Now this we have already seen, but we have seen its general name. What was the general name? Propionaldehyde, propiophenone. Like if there is CH3CO, so it is acetophenone, but this is known as propiophenone, but that was the general name. So let us now write the IUPAC. Sir, where is the functional group? Here is the functional group. So where you will find the main chain, here you will find the main chain. Why? Because double bond of benzene is actually not stable, it is resonance stabilized. So to the benzene ring, IUPAC says you just take it as a branch. So this branch is given a prefix called phenyl. So this phenyl is connected at what carbon, sir? Because this is functional group. So this is how you number the main chain. Obviously the main chain will be of this 3 carbon, with first carbon having the branch of phenyl. So 1 phenyl prop in 1 one, because first carbon is having the ketone only. So this becomes the IUPAC name. General name we have already seen, it is propiophenone. Moving to the some more examples of now. Actually in NCERT, from this chapter only, even NCERT asks you to remember the names of compounds having polyfunctional group, as in functional group, organic compound having more than one functional group. And from that chapter, although we have already finished it in NCERT, in GOC 1, I'm sorry, but why mains is in love with asking questions of organic compound naming having more than one functional group? Because NCERT allowed them, but NCERT allows them after this chapter of carbonyl compounds. So obviously we know, and if we do not, I'm telling you, among aldehyde and ketone, who is the senior functional group? Aldehyde. So we take ketone as a branch. So what about this one? Let us number the main chain. So this becomes 1 because it is aldehyde, hence given the priority of called a functional group. This is 2, this is 3, this is 4, and this is 5. So at third we have a functional group, but because ketone is a junior functional group, therefore now we'll be treating it as a branch. And for a branch, what we use prefix. So its name will be 3-oxo-pentane 1 ul. Although 1 is not written, but I'm naming it perfectly. So 3-oxo-pentane 1 ul will be the name of this compound. Talking about this one, now this is a substituted benzaldehyde, because at para position you have a group called nitro group, which is always treated as a branch. So you can say it is 4-nitro benzaldehyde or simply para-nitro benzaldehyde. What about this one? Now I said that when you use suffix called carbaldehyde, when the aldehyde is directly connected to the cyclic ring, but there is one more case when you can use the other suffix, that is suffix including the name of carbon in such examples. Why, sir? Because in such example, if you leave the carbon, then this will be a main chain. If you do not leave the carbon and think that no, we'll take that carbon in the main chain, then you will start your main chain over here, but in that case also you are leaving a same functional group of the same priority. So ultimately now you have to name this CHO as what? As a branch, but priority of, but these 3 functional groups are all same. So after 2004 amendment, it was amended by IUPAC that if you have to leave one functional group which is equally I mean, this is also aldehyde, this is also aldehyde. They are of equal power. So once you have equal power functional group, you do not take any of them as your main chain. In fact, give them equal ijjat, equal priority. How to give them equal ijjat? By taking this carbon as the main chain and considering what is your functional group, complete CHO group. So this is your functional group 1, functional group 2, functional group 3. So this becomes carbon number 1, carbon number 2, carbon number 3. So your main chain is of 3 carbons, so prop, because main chain is saturated, so ane. And at all the carbon 1, 2, 3, that means you have 3 and 3 what? Functional group with the name carbon, so it will be 3-carbaldehyde. A very beautiful example directly from NCERT. Moving to the next question. Now I hope I have already done this question in the table section. This is isobutyl ketone, but very famous example, therefore hence giving again. Now moving to the naming of carboxylic acids. What is the simplest acid? Sir, carboxylic acid of 1 carbon. From class 10th, you know, obviously it is methanoic acid, or technically methane-1-oic acid, but you can leave writing that one. And what is its general name? Very important, formic acid. 2-carbon acid is ethanoic acid with general name acetic acid. 3-carbon acid is propanoic acid with general name propionic acid. I'm focusing on the general name because obviously these names we know. 4-carbon aldehyde, 4-carbon acid is generally termed as butyric acid. Now, if I have an iso branch, that is first carbon, second carbon and a methyl branch, just like isobutyraldehyde, so here it will be isobutyric acid. But now, coming to dicarboxylic acid, what will be the smallest dicarboxylic acid? Sir, one COOH connected with another COOH. So this becomes your main chain. So it will be ethane. Its IUPAC name will be ethane 1,2 dicarboxylic acid. But here, sir, even over here 1,2 is not written because carboxylic acid can only be accommodated in the terminal carbon. So if I have whatever carbon chain and if I have 2 carboxylic acid, then the carboxylic acid will be at the carbon in the terminal positions. So that's why for dicarboxylic acid, as also if you do not write the number name, the location number, still you have to consider the COOH group on the terminal carbons. Therefore, here also NCERT is also telling you that you do not have to write 1, 2. So this becomes ethane dioic acid. Then obviously this is propane dioic acid, butane dioic acid, pentane dioic acid, hexane dioic acid. So all the dioic acid, even if writing their IUPAC name, you do not put the numbering of the branches because they will be existing in the terminal position. But again, very important thing is their general name. So simplest dicarboxylic acid is generally named as oxalic acid. 3-carbon dioic acid is known as malonic acid. 4-carbon dicarboxylic acid is known as succinic acid. 5-carbon is named as glutaric acid. 6-carbon dioic acid is named as adipic acid. Utter these names few times, you will also remember them. Now, again, like the aldehyde case, if I have a 3-carbon chain, so first carbon, second carbon and third carbon all having COOH, now we'll not say oic acid, we'll use the other suffix, and other suffix for COOH is the name only, that is carboxylic acid. So the name becomes okay, this is the general name. Its general name is simply carbylic acid or tricarbylic acid, and the IUPAC we have already seen propane 1, 2, 3, but over here tricarboxylic acid. But yes, it has a general name also. General name is tricarbylic acid. I mean, these general names are very famous. Now, if benzene ring contains COOH, this is known as benzoic acid. Its IUPAC name will be benzene 1 carboxylic acid, but obviously even IUPAC accept this name, which is benzoic acid. Now see, NCERT even writes it, although for most of the benzene containing organic compound, their general name is taken as the IUPAC name, but this NCERT also mentions over here that even this general name is considered as an IUPAC name. That's why it is deliberately writing benzoic acid on the IUPAC side as well. So now What about this one, sir? Obviously, this is an acetic acid, and the one hydrogen of this carbon is substituted by phenyl, so it can also be generally named as phenyl acetic acid. Obviously, you can do the IUPAC name. I'm less interested in the IUPAC name in whole of the chapter of carbonyl compounds. Obviously, you can observe this after the amount of time that we have spent over here. Again, ortho aldehyde in case of ortho dihydro di if in the previous slide we had no ortho position to aldehydes, so ortho position to carboxylic acid, so it is just also becoming like a thala, so it is generally named as phthalic acid. Actually it is what? It is benzene 1,2 dicarboxylic acid, the ortho isomer, but general name is phthalic acid. Now these are all some examples which I want you to make note and practice them. Now, after doing this example, sir, we have done aldehyde, we have done ketone, we have done carboxylic acid, but sir, we have not done the carboxylic acid derivatives. So that's why let us do them independently. So starting with, I have, let's say, what is the first acid derivative that we used? Acid halide. What is the very famous acid halide? Chlorides, bromides, generally they are used. So let me write Cl over here. If I write a hydrogen over here, it will be one carbon acid derivative, or whatever it is, any number of carbon atom it can have. Ultimately this is the functional group, so this will become your main chain, and here because this is the functional group, so it will become your carbon number 1 also. So what will be the name of this acid halide? Sir, if this main chain has some branch, then we'll name that branch in column number 1. If this main chain is cyclic, then we will name that by writing cycle in column number 2. But now here I am interested in just the name of the suffix. So in column 3 what you will write, sir? In column 3 we will write the main chain. So what will be the main chain, sir? Let's say it is alk, but this alk will be decided by RNC, and because this alk is right now we have taken it to be saturated, so column 4 will be ane. Now what about column 5, which I am more interested in? Obviously this is first carbon, so 1. So what is the suffix of this double bonded O with a chlorine? It is oil halide. So for chlorine it will become chloride. And if I have a senior functional group then obviously this complete thing act as a branch, and the suffix for COCl will be, this is carbonyl and this is halo, so it becomes halo carbonyl. So over here prefix for this will be chlorocarbonyl. But if a senior functional group is present, for all those students who are not familiar with IUPAC, I am again telling you, go to GOC1, just invest 30, 40, 50 minutes more, and over there you will find lot of practice questions also, because here I am coupling things together. So obviously we are clear with the first derivative of carboxylic acid, which is acid halide. Coming to the next derivative, if the C double bonded O is with this nitrogen. Now let me take one example for you, because obviously we have generalized, so let me take example. So let's say I have a CH3 over here, let's say I have one H over here, and I again have an ET. What is ET, sir? ET is representation of 2 carbon, C2H5. So this is an amide, although I have increased the degree of this amide, because just like amines, you can also increase the degree of this amide. So this becomes your acid amide. Now, how to name this acid amide, sir? Still functional group is here, so this will be your main chain. This will be carbon number 1, carbon number 2. I have a branch that is ethyl, but this branch is present on nitrogen, but branches are named at the column 1. So we'll start the name with nitrogen has a branch of ethyl, so N-ethyl. There is no other branch because main chain has no other branch, so column 1 done. Column 2 does not exist because main chain is not cyclic. Column 3 is, I have 2 carbons in the main chain, so eth. Main chain is saturated, so I'll write in, and at the first carbon I am having this functional group of amide. So what is the suffix of amide? Its name only, so it becomes amide. I hope we are clear with this. Now, if this carbonyl group is connected with halogen acid chloride acidamide. Next, if this carbonyl compound, I'm taking an example only, let's say CH3, CH2, I have the C double bond O, but now I am having not OH, I'm having an alkoxy group. So let's say it's O and it is CH3. So this becomes your ester. So how do you name an ester? Again, the process goes the same. For example, this is the functional group. So this becomes your main chain, carbon number 1, 2, 3. And this becomes a branch. What is the branch? Methyl. But in ester, sir, you will definitely have one branch. So in case in esters, we do not write that the branch is present in O, because we definitely know, because it is an ester, so this O will definitely have an alkyl group. So rather we write that alkyl group in the beginning without any number. For example, I have a methyl group over here. So without any number in column 1, I'm simply writing methyl with no mention of the branch. So you will think, arey, this branch is there, where this alkyl group will go? Hold on for a second. Column 1 done. Column 2 does not exist because main chain is not cyclic. What is column 3? 3 carbon main chain as in prop, because it is saturated, so ane. And first carbon is containing the functional group. What is the functional group? Double bonded O and O of the ester. So what is the suffix? Suffix is O8. Because it's a vowel, so this will be cancelled. So ultimately, if you find an ester, you will find an O8 at the end. So if you have an O8 at the column 5, you are confident enough that it is ester. So whenever it's O8 at the end, it will have an alkyl group without any numbering at the beginning, and that alkyl group you directly connect with that oxygen, making it an ester. So I hope we are clear with the rules of naming esters. And last but not the least is naming of the acid anhydrides. So for example, I have this CH3, C double bond O, OH. Sir, but this is carboxylic acid. This is what carboxylic acid? Ethanoic acid. On the other side, let's say I have, again, obviously I have this carboxylic acid. Let's say it is one carboxylic acid as in methanoic acid. Now, as I've told you, how you can create acid anhydrides, sir, by dehydration. So you take any dehydrating agent like concentrated sulfuric acid or any dehydrating agent like P2O5. Ultimately, dehydrating agent is going to remove water. So if this water is removed, you tell me what are you left with? CH3, C double bond O on left side, and the pink colored, so let me write it with the pink color. So and the pink colored O, that means another carboxylic acid on the another side. Obviously, you will be in examination, if at all you are asked about the IUPAC, you in examination you will be given such group. So what to do? Just think in your head by putting a line. Put H on one side, OH on other side. It will be quite visible to you what is this carboxylic acid, what is that carboxylic acid. Name the carboxylic acid and just do not write acid. Like this carboxylic acid name is ethanoic acid, its name is methanoic acid. Which comes first? E. So what will be the name of this anhydride? First you write ethanoic, do not write acid. Then you write methanoic, and at last just write anhydride. So this is how you name an acid anhydride. So I hope we are clear with this also. Moving to the next. Okay, now as I was telling you, you will find so many problems. So discussing the problems, now this is a JEE Mains 2024 question, and I guess this vanillin compound, vanilla beans, I hope you remember this structure, a directly JEE Mains question. If I have aldehyde over here, then at third carbon I was having a methoxy group, and at fourth carbon I was having this alcoholic group. Remember, we have read these just in the previous slides. So very important examples. So what are we asked in the question? That sum of oxygen atoms and pi electrons. So let me make the pi electrons with another color. So this is 1, 2, 3, 4. So pi electrons. Okay, not bond, electrons. So this is one pi bond will have 2 electrons, so 4 will have 8 pi electrons. And what about oxygen atoms? Obviously it is quite simple. If you just know the formula, question is quite easy for you. So 8 and 3 is definitely C. If you just know the NCERT fact, you are going to tick the answer. So this is an integer type question, and your answer will be will be 11. So let us attempt this question. I hope you can find answer to it as well. So I hope such questions make you feel the power of NCERT. Now this JEE Mains 2024 question you can even do from your class 10th basics, but you should be comfortable with NCERT. Then only such questions will be very probable for you. So we know for formic acid for carboxylic acid, what is the smallest acid? Sir, the smallest acid is formic acid. That means CH3, C double bond O and this OH. So what is the molecular formula? Sir, I have one carbon, I have 2 hydrogens and I have 2 oxygens. Now if I want to make a homologous, this is the first member of the homologous series of carboxylic acid. If I add one carbon, as in if I make this carbon as C and then H2, that means I have added a CH2 unit. So this carbon from 1 and 1 becomes 2 carbons. So 2 carbons, 4 hydrogens and 2 oxygens. That means option 2 is your correct answer, C. Such questions are coming. Now coming to the next question, the number of compounds given below which contains carboxylic acid group is. So we have some options, and for this now you should know NCERT through the depth. So what is sulfonylic acid? We'll be dealing this in the chapter of amines, but I hope most of you know this. What is sulfonylic acid? Let's say I have an aniline and I have sulfonic acid over here. What is sulfonic acid? SO3H, so double bonded O and H. Now obviously we know that it exists in the form of zwitterion. If you do not know this, then in the chapter of amines we will be discussing this. So this ammonia derivative of benzene sulfonic acid is known as sulfonylic acid. So although it is definitely a very strong acid, but not not containing any COOH group. So to us we are asked that compound should contain COOH. So this definitely do not contain COOH, so not an answer. Picric acid, we definitely know this is phenol, then 2,4,6-trinitrophenol, so it is also not having any COOH unit. Now aspirin we have seen in the chapter of alcohols, in the topic of esterification, that once phenol reacts with acetic anhydride, so this carboxylic acid group remains as it is, but the phenol derivative, the phenol loses its hydrogen and acid derivatives loses the acetyl group, and this compound, this ester you get, although the functional group is still carboxylic acid. So this is your aspirin, and this aspirin is definitely containing the COOH group, therefore this will be our answer. What about ascorbic acid? A very famous organic compound given in the chapter of biomolecules. It is actually vitamin C. So because it is a concept of biomolecules, so giving you this. Now this is the structure of aspirin. Now for some students it is quite difficult to remember this, so I am giving you a trick to remember this as well. How to remember it? You just think of a 6-membered carbon chain. Sir, how? A 6-membered carbon chain, as in 1, 2, 3, 4, 5, 6. And actually this ascorbic acid also contains carboxylic acid, but this is the carboxylic acid, double bond O and OH. Now what happens is it also undergoes dehydration, but within the molecule esterification takes place. So this carboxylic acid loses OH, and what is the alcohol? Actually this is first carbon, second carbon, third carbon, and this fourth carbon also having OH. So this loses hydrogen and this loses water, and you get a cyclic chain. Let me number that cyclic chain for you. This is first member, second member, third, fourth and fifth. I hope you can see a 5-membered ring structure. Now this is the first member, this is the second member, so obviously this is the carbonyl group, but this is a conjugate. How you will remember this? This is a conjugated alkene, so pi sigma pi, and all the carbons, all the remaining carbons has OH. OH of this carbon has been dehydrated, but these I said all the carbons must have OH. So if you know this, if you learn ascorbic acid structure via the esterification mechanism, it will be much easy for you to remember this structure. Although because it is asked in JEE, this is a JEE Mains 2021 question and has a very nice possibility of coming in the later examination also. That's why, although our answer was very easy, but you should know the structure of ascorbic acid as well, which essentially do not contain carboxylic acid group, because carboxylic acid group undergoes esterification and you get a cyclic ester. So moving to the next question. The next question also, I mean the application of general organic chemistry, the naming that we have just read. Now let us see what is the functional group. Obviously we can see this is the carboxylic acid and this becomes our carbon number 1 because this is the senior most functional group. Then this is carbon number 2, but this carbon number 2 is having a branch because now this functional group will be treated as a branch because carboxylic acid is the most senior functional group. So this is branch of aldehyde. So with carbon, the carbon CHO branch is termed as formyl group. Now this is third carbon, this is fourth carbon, which is again having a hydroxy branch, although alcohol is a functional group, but because carboxylic acid is a senior functional group, so it is treated as a junior functional group. And for junior functional group, what we use? Their prefixes. So this becomes carbon number 5, 6 and 7. So I have a 7-membered ring with 2 branches. This is hydroxy starting with an H. This is formyl starting with an F. So what comes first? F. So second carbon is having formyl. Second carbon is having formyl. 4 is having hydroxy. Then I have a 7-membered ring. So hept. 6, 7 has double bond. So 6-ene. So 6-ene. Okay. Over there I have a point of difference. So this becomes wrong. This becomes correct. I hope it is quite clear, but a very, very probable question for our paper to at least read and learn things through logic. Now, this is again, okay, it is hidden. This is also a 2021 question. Now, general names of carboxylic acids. Actually, if you have this dioic acid, sir, what dioic acid? I just make that dioic acid for you. Very famous dioic acid, the geometrical isomers. Now, if I have a double bonded carbon and I have COOH group opposite to each other, so this becomes a trans isomer. The name will be, it is a 4-carbon chain, so name will be bute, obviously 1, 2, 3, 4. So bute 2-ene 1, 4. You do not even have to write that 1, 4, but writing it specifically. So 1, 4 dioic acid. But this is what isomer of this bute-2-ene? It's a trans isomer. So this trans isomer is also known as generally fumaric acid. Very important name. Please do remember this. And obviously we know that trans isomer has lesser boiling point because the dipole moment of this trans isomer is cancelled. So it has a lesser dipole moment than whom? Than the cis isomer. What will be the cis isomer? This C double bonded C, this C double bonded O with an OH, this C double bonded O with an O and an H. Obviously you can see this cis form will have a dipole moment, but it will also have a property. What? Of undergoing dehydration. Why? Because whenever 5 or 6 membered rings are formed, then those cyclic structures are very stable. So it also easily undergoes dehydration and a cyclic anhydride is formed. And this cis form of this bute-2-ene dioic acid is actually generally named as this general name, which is maleic acid. Very important name. Please do remember this. This cis form is termed as maleic acid. And because this anhydride is formed with this cis form of bute-2-ene dioic acid, so you are asked that how can it be prepared? Sir, we know carboxylic acid undergo dehydration and form acid anhydride, and if one carboxylic acid has 2 carboxylic acid group, then it can go self dehydration, but trans isomer can't have self dehydration because cyclization is not possible, but cis isomer can undergo cyclization easily, and therefore what will be your answer? So heating cis butene dioic acid. I hope it is quite clear and a very probable question, logical question, a good question to practice. Now sir, we have done IUPAC. Yes. So IUPAC of aldehyde, ketone and carboxylic acid done, but they show isomerism also, and we know what famous isomerism they show. They show functional isomerism. Apart from function, because all of them are functional isomers of each other because they have different properties. So obviously you can if they have same molecular formula, you'll get number of questions in which it is just asked that what type of isomers they are, and we definitely know they are functional isomers of each other, but they show some other isomerisms as well, and for them obviously I have discussed them in detail in GOC, but here I'm taking those questions so that you can revise for your mains point of view questions. You can I mean it is more than sufficient. So moving to the next question, discussing about the isomerism. So the question is, this is again a question from 2024. You have to say which is metamer. Now what is metamer? When the functional group remains the same, as in functional, you should not be a functional isomer, then only I can term you a metamer. And the functional group is a polyvalent functional group. Like for example, I have a acid amide over here, so I have one alkyl group over here, one alkyl group over here, and if the nature of alkyl group changes, as in number of arrangement of carbon changes, and whatever isomers we get, those isomers are not termed as chain or position isomer, they are termed as metamers. So this is amide, this is also amide. No, here functional group is changed. So when functional group changes, it becomes a functional isomer, not a metamer. So directly cancelling this. This is also amide, so good. This is also amide, so good. But one is benzene, one is cyclohexane. So benzene, even molecular formula will not be same. So this is gone. Cyclohexane, molecular formula will not be same, so this is gone. So I hope without much of a problem, you can say that they are metamers of each other, specifying the definition of metamerism. Two compounds having same molecular formula, same functional group, but different nature of alkyl group along a polyvalent functional group. Now over here it is a divalent functional group. The next question is again, which of the following pair? Again, see, metamerism is very much loved by JEE. So this is again a JEE 2021 question. You are given options. Now it has, apart from benzene, it has 2 carbon. Apart from benzene, it has 3 carbon. So molecular formula is also not same. So no point of checking it to be an isomer. Similarly, it is a 5 carbon. It is also 5 carbon, but they are chain isomers because size of main chain is changing. You should have a functional group. And what type of functional group? A polyvalent functional group, at least a divalent functional group. Along that functional group, if alkyl group nature changes, then you are metamer. This is having no functional group. So this is just simple chain isomer. So because it is a chain isomer, that means not a metamer. So not an answer. Now, obviously this we can see, this is 1, 2, 3, 4, 5, 6, 7. So a 7-membered ketone. And what about this one? 1, 2, 3, 4, 5, 6, 7. So molecular formula same, and it having 3rd carbon is having ketone and 4th carbon is having ketone. That means along this ketone. Now here I will not say it is a position isomer, although the definition of position isomerism is also valid, but you ignore chain and position when metamer definition is valid. And because ketone is a divalent functional group and nature of alkyl group is changing, so it becomes a perfect example of metamer, and when metamer definition is validated, you do not say it is chain or position. Now, what about this one? It is having, apart from benzene, it is having 2 carbons. Apart from benzene, it is having 2 carbons. So yes, molecular formula is same. And what is different? Just this OH position. So this is in fact a positional isomer, but we are asked metamers, so not an answer. So see, we have revised whole of the structural isomerism with this just one question. Moving to the next question. Now, apart from functional isomerism and tautomerism, apart from functional isomerism and metamerism, one important isomerism shown by carbonyl compounds is the phenomenon of tautomerism, the keto-enol form. Generally, keto form is more stable, enol form is less stable, because in enol form double bonded carbon, which is electronegative, is bonded with OH. So enol generally is not stable, but It can become stable if it gets some extra stability. Like for example, I'm just taking this very beautiful example. For example, this is a ketonic form, but if the carbon next to this carbonyl carbon is the alpha carbon, if this alpha carbon who's having one hydrogen, if this hydrogen undergoes tautomerism, then let us see what we get. How we draw tautomerism like this, which represents that equilibrium is unequal, because over here some of the generally maximum of the concentration is focused on the keto side, and very less amount of enol we generally gets. But let's say what is the enol. Let us see what is the enol. So if this hydrogen goes to this oxygen, then the double bond will come over here. This will result into the formation of the cyclic ring will remain as it is. It has been just now introduced by this pi bond, and this double bonded oxygen has just now become single bonded OH because hydrogen has been migrated. Now if we do this over here also, as in this CH, so hydrogen going to this and double bond coming over here, so this will lead to the formation of some structure like this, an enol form of this sort. And at last let us do it for the third one also. So I hope it is quite clear to you. Sir, now these pi bonds are in conjugation with each other, resulting into the formation of an aromatic ring. And aromatic compounds are not just stable, they are very, very stable. So because of this aromatic stabilization, generally enol form is not produced, but such aromatic stabilization can create more percentage of enol form, so it is a more stable enol form. And therefore this keto form will not exist in nature. This compound will exist as this enolic form of aromatic alcohol called tri-substituted hydroxy group of hydroxybenzene. So very stable. And in the question you are asked which is having highest enols, obviously this will have the highest enolic content. A very beautiful example. Generally tautomerism is asked by advance, but I hope it is quite clear to you that how can we have its application with just using some common senses of our NCERT only. Moving to the next topic, the actual topic from where we start carbonyl compounds. So how do we study organic chemistry? First we know we get questions from IUPAC and isomerism. Done. After that, preparation. So we have how many compounds we have? We have aldehydes, we have ketones, and we have carboxylic acid. But carboxylic acid and their derivatives we will be doing in the, like NCERT, we will also be doing later. So first dealing with aldehydes and ketones. So preparation of aldehydes and ketones. Actually aldehydes and ketones, we definitely know they are different functional groups, in which aldehyde is a senior functional group. So there are, NCERT also lists them, JEE loves them, there are set of method of preparations. But first set of method of preparations are those in which you produce aldehydes and ketones both. As in these are the method of preparations. You have to memorize them. You have to remember them like your trigonometry formulas, because they will be n number of time they will be used even for your class 12 boards conversion questions, and those conversion questions are also valid for JEE mains and JEE advanced. So keep these reactions on your tips. So preparation, what is the first preparation that we are dealing? Preparation of, these are those preparations which will which will produce aldehydes and ketones both. So the first, now this will also help you to actually have this essence that organic chemistry is very easy. Why I'm saying that? Because now whatever you have studied in the previous chapter, alcohols of reactions of alcohol will now be treated as preparation of our carbonyl compounds, because some of the reactions of alcohol could produce carbonyl compounds. So the very first preparation of producing aldehyde and ketone both is by oxidation of alcohols. We know if I have a 1 degree alcohol, I can oxidize this 1 degree alcohol and either form aldehyde or acid. How can we form an aldehyde? If we use a mild oxidizing agent, because mild oxidizing agent will convert only one C bond H into OH. So one C bond H converts into OH two OH on one carbon is unstable. And how does that compound stabilizes? By dehydration, leading to the formation of aldehyde. But if I have a strong oxidizing agent, then whatever hydrogen has been left behind, strong oxidizing agent will do that C bond H, changing C bond H into H, will do it one more time, because it is a strong oxidizing agent. It can do the action multiple times because it is strong. So this H will also be replaced by OH, so you get your carboxylic acid. Similarly, if I have a 2-degree alcohol, then what does oxidizing agent do? It can only oxidize C bond H. And what C bond H? Which is already polar, because only this is polar. So only this carbon can undergo oxidation, and because this compound is having only one C bond H, so you use mild or you use strong, you use any oxidizing agent, it will lead to the formation of ketone only, because oxidizing agent action is not so strong that it can break C bond C. So generally, strong oxidizing agent, generally no oxidizing agent can break C bond C. That means your ketone can never undergo oxidation. No, they can undergo oxidation, but under vigorous condition. And question always specify that ketones are undergoing oxidation in a vigorous condition. So whenever they undergo vigorous oxidation, then only you will oxidize ketones. So how to do that? We'll do them separately in a rule called Popov's rule. But going by NCERT basics, I hope we are clear till this. Now, similarly, if we talk of 3-degree alcohol, this 3-degree carbon is not having any C bond H. That means even if you use any mild or strong oxidizing agent, it will result into no further oxidation. So you will have no reaction. Now, what are the list of these? This we have already seen in the chapter of alcohols. So quickly, although for advanced there is a big chapter of learning all the and many oxidizing and reducing agent, but for JEE mains, for boards, and I am telling you, most probably 50 to 55%, this is more than sufficient for your advanced paper also. So what are the very famous oxidizing agents? You should remember 2 oxidizing agents as mild oxidizing agent. First being PCC. PCC is pyridinium chloropromate. It is a complex formed by CrO3, pyridine and HCl. So this PCC in question is just simply written as PCC, so acting as a mild oxidizing agent. Focus on this CrO3 because this CrO3, when present in any anhydrous medium, precisely when the medium is pyridine, then CrO3 in presence of pyridine is also mild oxidizing agent, and it also has got a name. It is also generally named as Collins reagent. These are the famous 2 mild oxidizing agents. Coming to the list of strong oxidizing agent that you know from your class 10th, KMnO4 in any medium, acidic, basic, neutral. K2SAT7 acts as an oxidizing agent only in acidic medium, and a very beautiful example from NCERT, that is Jones reagent. Now, what is Jones reagent? Collins reagent is nothing but Jones reagent also. How, sir? Because Collins reagent is taking CrO3 in presence of pyridine, and Jones reagent is taking CrO3 in acidic medium. So if you take CrO3 in acidic medium, that chromium only act as a strong oxidizing agent and undergoes strong oxidation. What does strong oxidation do? I hope we have already covered that. Now, sir, oxidation is addition of oxygen, and dehydrogenation is removal of hydrogen. So if I give you oxygen, you will get oxidized. If I remove hydrogen, you will again get oxidized, so the product will remain the same. But actually, oxidizing agent are doing addition of oxygen, and there are some reagent which can remove hydrogen. So removal of hydrogen will be technically will be termed as on the basis of English language. If I remove hydrogen, it is termed as dehydrogenation. What is the famous dehydrogenating agent? Heated copper. So if you take copper at 300 degrees Celsius, it removes hydrogen. So with 1 degree alcohol, if you remove hydrogen, remove one H and another H, so H2 is removed, so you're left with aldehyde. So with 1 degree alcohol, you always get an aldehyde. With 2 degree alcohol, you always get a ketone, because with mild oxidizing agent, you get this only. But even mild oxidizing agent sometimes can do a little bit of strong oxidation. if you have taken them in a higher concentration. But so in conversions also, if you want to convert, if you just have to do mild oxidation, then instead of using mild oxidizing agent, preferably in industry also what we do is we do dehydration using heated copper. One more important point about this, generally 3-degree alcohol do not undergo oxidation. But if we take 3-degree alcohol, because this is not adding, this is removing. So because it is not having any hydrogen, but because I have taken heat, so in presence of heated copper, this 3-degree alcohol do not give no reaction. It gives reaction, although not the similar reaction. It undergoes dehydration. Is a very nice industrial fact, because this elimination happens via even mechanism, and I hope even mechanism we are very much comfortable. Sir, this alcohol will be gone, creating a carbocation over here, and post formation of carbocation, hydrogen of beta carbon will be removed. Let's say this one hydrogen is removed, and you get a beautiful double bonded system. So ultimately OH and H, dehydration takes place. So post this dehydration you get an alkene. With strong oxidizing agent we say no reaction, but over here we are saying dehydration. Moving to the now let us revise what are the methods. Sir, preparation of these are the methods by which you can form both aldehyde and ketone. What is the first method? Oxidation of alcohol. What is the second method? Dehydrogenation of alcohols. What is the third method? Again, we have done this also in the chapter of hydrocarbons, by ozonolysis of alkenes. What is an alkene, sir? We definitely know this double bonded system. First we react with ozone. This intermediate is formed called the monoozonide. Now we can break these bonds, so this oxygen is gone, and this carbon and this carbon, both carbons have this double bonded oxygen attached with it. But NCRT only signifies reductive ozonolysis. For example, if to this ozonide I remove oxygen, so what I'm doing reduction. So what is the reagent for a reductive ozonolysis, which is 95% of the time JEE mains ask only reductive ozonolysis mains. So what is a reductive ozonolysis? Remove this oxygen. How to remove it? Either use zinc and water, either use dimethyl sulfide. These are some reagents. Maximum, most of the time you see zinc and water. What does they do? They do reductive ozonolysis. What does reductive ozonolysis do? Simply break this double bond, add the one double bond O on this side, one double bond on that side. So obviously the corresponding carbonyl compounds you get. But if you do oxidative ozonolysis, so first you need to know what is a reagent. So do not use any substance which can remove oxygen. Rather use simply hydrogen peroxide, which is an oxidizing agent. So post use of this oxidizing agent you get oxidative ozonolysis. So what is the difference? Ultimately you are getting this product only, but oxidative ozonolysis works as a strong oxidizing agent. What does strong oxidizing agent used to do? Strong oxidizing agent cannot break C bond C. It can't break C bond C. Oxidizing agent just has a property of converting C bond H to C bond OH. This polar carbon is not having any C bond H. So ketone will remain as it is. So this is not changed. This is the same. But this is an aldehyde with this one hydrogen. And oxidative ozonolysis do what? Function of a strong oxidizing agent. So this C bond H will again be replaced by C bond OH. So instead of this aldehyde, post oxidative ozonolysis your product will be corresponding carboxylic acid. Because now this is what you should know by NCRT of class 12th, but because we are going to do mains, so again revising, making you revise that hydrocarbon basic. What hydrocarbon basic? So it's a revision. It's an alkene. Ozonolysis we have just discussed. What is the most famous ozonolysis? Reductive ozonolysis. How to do it? See the double bond, break the double bond, add a double bonded O. So this becomes a 2-carbon aldehyde as an acetaldehyde. That becomes a 1-carbon aldehyde. That means formaldehyde. I hope it is clear. Now, if I use a strong oxidizing agent like any of these, or now I know one more option, which is oxidative ozonolysis. That means if I react with oxygen followed by treatment with H2O2, then what happens? Again, this much is done. But further oxidation, so go to this polar carbon, this carbonyl carbon. Is it containing one hydrogen? Yes. So replace this by OH, corresponding acid. It is having two hydrogens. So oxidizing agent is a strong oxidizer. Strong oxidizing agent will not leave any C bond H. If you have 1, 2, 3, whatever, this carbonyl compound, whatever C bond H it is having, strong oxidizing agent will not leave any C bond H. So because it is having 2 C bond H, so it will be getting 2 OH. But sir, you said one carbon having 2 OH is not stable. So dehydrate it. So if it also undergoes dehydration, so this is water and this remaining compound is CO2. So actually you are not going to get a liquid product. This carbon will be going away in form of gases, CO2 gas and water vapors. So I hope you are clear with what does oxidative ozonolysis and strong oxidizing agent do with an alkene. This we have already done in the chapter of hydrocarbons, and because we are talking of oxidation of alkenes, so while leaving this the practical organic chemistry logic, I hope we remember that if I have this KMnO4, but if this KMnO4 is taken in a cold, aqueous and dilute medium, then this cold, aqueous and dilute KMnO4 is also known as Bayer's reagent, because KMnO4 has a very dark color, and that dark color is because of the presence of MnO4 minus. Once it reacts, color disappears. So disappearance, decolorization of dark color of KMnO4 is a test of unsaturation, because we have reduced the concentration of reagent to a very small extent, but still it is a strong oxidizing agent. So it can only break the weakest bond. The weakest bond is the pi bond. So because alkene is having only one pi bond, it can't break the sigma bond because concentration of KMnO4 is too low, temperature is also too less, so only pi bond will be broken, and instead you will form a vicinal diol, as an OH on the adjacent carbon having the double bond. So this vicinal diol is your major product once alkene reacts with Bayer's reagent. So this is not there in this chapter, but I'm again saying this is a revision, because we have just discussed the ozonolysis of alkene. So discussing all the oxidation undergoing alkene, which we have seen in the chapter of hydrocarbon, but we need revision. So we are giving you everything at every point of time, again and again. Going to the last method of preparation, which can create both aldehyde and ketone. The last one, the D, is hydration of alkyne. Now this also we have done. In revising it, so let's say I have an alkyne. Now if I take water, I have to use some catalyst, because alkynes undergo hydration in the presence of few drops of concentrated H2SO4 and HgSO4, giving these H plus and Hg2 plus as the electrophile. Now what does electrophile do? Electrophilic addition. So once H plus will attack, you will form a carbocation. Where carbocation will be formed? Where it will be more stable. So those Marconi-Koch rule will also come into, but as again in hydrocarbons also I told you, don't learn a Marconi-Koch, go by basic. So where carbocation relatively is more stable? Here. So this will get H and this will get OH of water. So rather you form this intermediate. Why I am saying intermediate? Because double bonded carbon having OH is not stable. Why? Because this is an enol form. So again an application of tautomerism in the chapter of in the content of NCERT. So it again undergoes tautomerization. How, sir? This alkene double bond will come over here and hydrogen will be going to this carbon. So this carbon becomes CH3, bringing the carbonyl group over this carbon. Hence, if this R is a hydrogen, it can be an aldehyde. If this R is a alkyl group, it can be a ketone. So these are the preparations by which you can make both aldehydes and ketones. Moving forward. So please allow me to add just one more reaction to our memory base, because we are already discussing the oxidation of alcohols. So one more oxidation that is not there in NCERT but valid for good questions, even for JEE Mains, advanced loves it, is an oxidation of specifically 2-degree alcohols known as the Oppenauer oxidation. Now, in order to have this open-air oxidation, what is utilized? The oxidizing agent is a mixture of aluminium tertiary butoxide along with acetone. For remembering, it is very easy. Like if you have a 2-degree alcohol, then this alcohol gets oxidized to corresponding ketone, and because this has got oxidized, so it is oxidized by whom? Specifically, the another reagent, that is acetone, gets reduced to form the isopropyl alcohol. Now, this is a highly specific reaction which only oxidizes 2-degree alcohol. So even if you have any olefins, as in any double bond, that double bond is not even reacted with this reagent. For example, if I have this 2-degree alcohol, although I know this 2-degree alcohol is an allylic alcohol, but still it selectively oxidizes only this 2-degree alcohol and will not disturb the double bond. Therefore, double bond is as it is, and the 2-degree alcohol has been oxidized to the corresponding ketone. A very specific reaction, although because we are discussing it, so just allow me 30 more seconds to give you the exact mechanism. We know this oxygen is electron rich, so acting as a Lewis base, it reacts with Lewis acid, aluminium. As soon as aluminium receives electron, this one alkoxide is gone, and oxygen will attain a positive charge, so deprotonation will make oxygen also neutral, resulting into the formation of this intermediate. Now, as soon as this intermediate is produced, now acetone will function and will do what? Acetone will give away the electron to aluminium, resulting into the formation of this ketone. Now, how this ketone is produced? By this hydride transfer, and as the hydrogen is removed in form of H minus, it will be given to this positivity of the carbonyl group. Hence, this acetone is getting reduced. Post reaction with aluminium tertiary butoxide, hydrogen will be coming to this oxygen, and the tertiary butoxide group will be going to the aluminium tertiary butoxide, and you will be again getting the reactant. So ultimately, what is happening over here? The 2-degree alcohol is converted into an alcohol, so into a ketone. That means it is oxidized, and the corresponding ketone, which is acetone that we have used, is reduced to isopropyl alcohol. Although the mechanism you can leave, but this open-air oxidation is also one of the very important methods. So moving forward, we can also prepare both these aldehydes and ketones with this last method, not there in NCERT, but important, by carboxylic acids. Now, first, if I have a salt of carboxylic acid like calcium salt or barium salt, and you just heat it, dry distillation of such salts of carboxylic acid do what? Because calcium carbonate or maybe barium carbonate, they are precipitated salts, so they get precipitated, and Le-Chatelier's principle forces the equilibrium to shift in forward direction. Like for example, I have a calcium formate. Now, how can you write a calcium formate via its structure? I hope it is quite possible and clear to us to write the structure of the salt. Now, why? Because now I will be using a dabba method. What is that dabba method? I'm encircling the atoms that can produce a precipitate. Precipitate will be calcium carbonate. So as this CaCO3 solid has been precipitated, it will force the equilibrium to shift in forward direction, and therefore what we are left with just this hydrogen and this carbonyl group along with this hydrogen. So obviously now these bonds will be added, and they will result into the formation of product. So this is a carbonyl group attached with an hydrogen, so hydrogen attached with a carbonyl group, so this is nothing but your simple formaldehyde. Sir, that means the percentage yield of such reaction will be very high. Yes. So industrially, actually, these carboxylic acid salts are heated, and dry distillation gives you either aldehydes or ketones, depending on the salt of carboxylic acid that we are using. Like for example, if I would be having, instead of this H, I would be having CH3. So this will be calcium acetate salt. So if calcium acetate salt is subjected to heat, then this will be CH3 and this will be CH3. So this will be CH3 and this will be CH3, resulting into the formation of beautiful acetone. So you can produce acetone as in ketone also, and over here I have produced aldehyde. So obviously this method can be used to prepare both aldehydes and ketones, hence discussing over here. Now let's say I have a mixture of salt, then mixture of salt will produce what? Sir, obviously we know, I'm just telling you what we have already done. So this CaCO3 gone, so you can also have formaldehyde. Over here, if CaCO3 is gone, then you can have acetone. So obviously, what are the products that you can get? Acetone and formaldehyde. So formaldehyde you can obviously obtain, plus acetone you can obviously obtain, but they will be self product, as in when one molecule reacts with the similar molecule and releases calcium carbonate. But what I'm saying is, although they will be produced, but they will be minor product. Sir, why? Because you tell me stoichiometrically, if I have taken, let's say, 100 molecules of this and 100 molecules of this, so stoichiometrically they both can react to a larger extent. So when they both react and result in the formation of a salt, then what is produced? So for that, I hope I need actually 2 moles of calcium carbonate. So let's say CaCO2 I'm getting from here, so rather I should remove these. So you just do the stoichiometry. This is CaCO2, so I need, in order to have 2 moles of calcium carbonate, what I should have? This is 1 Ca, this is 1 CO2 taking oxygen from there, this is another Ca taking CO2 from here and oxygen from there. So ultimately this Dabba method is letting you understand that 2 moles of calcium carbonate is gone, resulting into the formation of what? This hydrogen is getting bonded with that carbonyl group. So that means what else you have? You have a cross product, and the cross product is nothing but acetaldehyde. And this acetaldehyde will be produced in a larger amount. Why? Because whenever you have a mixture of product, then calcium carbonate, obviously the salt will be precipitated. But what product will be formed in a larger amount? The cross product. So similarly, sir, what if we do not have a salt? Can we heat directly the acids? Yes. Whatever fatty acids you can vaporize, generally fatty acids vaporizes at around a temperature of around 300 degrees Celsius. So there is also a dehydrating, there is also I would rather not say dehydrating agent, because actually you can remove carbonic acid, H2CO3, but you do not, for removing H2CO3, I'm not making carboxylic acid salt. I'm directly using carboxylic acid vapors, heating them at a temperature of 300 degrees Celsius and in the presence of manganese oxide. Although it is an expensive catalyst, but still, in order to prepare high percentage of aldehydes and ketones, vapors of carboxylic acid are directly heated in presence of manganese oxide. The reaction is almost the same. Like for example, over here we were getting precipitate of CaCO3, and here we'll get vapors of CO2 and H2, because H2CO3 is carbonic acid which is unstable, and that unstable acid decomposes to form H2O and CO2. So sir, show us H2. This is OH, and just add the molecules. I hope you will be clear with H2CO3, H2CO3. Now I hope it is clear to you. Let me help you with it. Now this is this C, 2 oxygen and third oxygen, so H2CO3. Now H2CO3 is carbonic acid. Carbonic acid is, although it's a weak acid, apart from being weak, it is unstable also. So if carbonic acid is produced at a temperature of 300 degrees Celsius, what it creates, it gets removed as gas, H2, add them, this is H2CO3. So what are we left with? So this and this. That means we have again formed a formaldehyde. Sir, what if mixture is produced? What if I use a mixture, as in, what if I have this only, but I'm using a mixture? So again, you will have to use the removal of H2CO3. So once H2CO3 is gone, what is the product that we are getting? CH3, then this carbonyl group adding with this hydrogen. Obviously this is acetaldehyde, and like over here, because I have mixture of two acids, so I'll be getting three products, but the cross product will be formed in a larger amount. So I hope we are clear with this last method of preparation of aldehydes and ketones both. Moving forward, moving to those methods of preparation which can only produce aldehydes. Now all these are NCERT based reactions, so if you try to find questions around them, then you'll not find one, you'll find many examples just explaining this. So make note of it, they are very important NCERT naming reactions. So the first reaction which can only produce aldehyde is the classic Rosenmund reduction. Now what does Rosenmund reduction do? Actually it takes what as a substrate? Acid halide. Now any acid halide, either aliphatic or aromatic acid, generally what halide we use is acid chloride. Now what we have to do is we have to add hydrogen, so we have to reduce this acid halide, and in order, if you reduce, we get corresponding aldehyde. But we know that while we were doing oxidation, alcohols used to get easily oxidized even with mild oxidizing agents. So similarly, while reduction, if you have an acid or acid derivative, they can also be easily reduced to form alcohol, but we have to stop the reaction in the intermediate step at aldehyde, at the carbonyl stage. So we have to do partial reduction. And how come this partial reduction is done? For hydrogenation, we need a catalyst like nickel, platinum, palladium, because without them we cannot start reduction. But in order to initiate the reaction, we have used a catalyst. So Rosenmund specifically use palladium as a catalyst. But in order to reduce the reducing power of palladium, so that complete reduction can't take place and partial reduction should take place, we poison the catalyst. How do we poison it? You can either use any sulfur compound like barium sulfate, you can either use calcium carbonate, or you can either use quinoline. So any of this can act as a catalytic poison. You have to boil this in a xylene solvent. Now this complete mixture, as in poisoned palladium, is known as Lindlar's catalyst. Now I hope we remember that this Lindlar's catalyst also used to reduce alkynes, so we'll revise that also. But ultimately, if we use this poisoned catalyst, then we will get the corresponding aldehyde only, either aliphatic or aromatic. Now let us understand this with an example. So obviously we have pent 3 in 1. So pent as in how many, what is the number of carbon present in the main chain? 5. Now let us decorate it. It is having, at first carbon, it is having an acid chloride. So let's say this is the first carbon. I have made it an acid chloride. Now at third, this is first, second, third. So between third and fourth carbon, I should have an alkyne, because it is saying 3-pentyne. So this is first carbon, second carbon, third carbon, fourth carbon, and fifth carbon. So between third and fourth, I am having an alkyne. Now we are reducing this. Now remember, this poisoned palladium is known as Lindlar's catalyst, which also reduces alkynes to form cis-alkene. How to remember it? Giving poison is a bad thing, bad gives cis isomer. Although this is a regio selectivity, but in order to be just quick with the questions, how do we learn it? Giving poisonous is a bad thing is a sin creates a cis isomer of alkene. So this alkyne reduces to an alkene. So let us form an alkene with what? with a cis configuration. So I'm adding hydrogen on the same side. Now coming to this third, fourth alkyne, which has recently become cis. So this will be a methyl group, and over here I'll be having this second carbon. So that means CH2. Now this CH2 is connected with this carbonyl group, and this carbonyl group should also get reduced, that we have just studied. So this CH2 is connected with a carbonyl group, and that carbonyl group has been recently introduced by this nascent hydrogen, the reducing hydrogen, which is also provided by the Lindlas catalyst. So this is our product. Let us name this product, carbonyl being the functional group, being the first carbon, so second, third, fourth and fifth. So this is an alkene, but what alkene? Cis form of alkene. So writing cis in the beginning, and after that the IUPAC name. Now it is not having any branch, it is having a 5 carbon chain, so it becomes pent, then 3-ene, and at first carbon I have a functional group called aldehyde. Vowel will get cancelled. So this is your product, which obviously revises us the theory of alkyne producing cis alkene. This was the first preparation which you can only use to prepare aldehydes, the Rosenmund reduction. Coming to the second method of preparation which can only produce aldehyde is the classic naming reaction called stiffen reduction or stiffen reaction. Now what is stiffen reagent? It is stannous chloride, SnCl2 in presence of HCl. Now SnCl2 when reacts with HCl inorganically, it will form what? It will form SnCl4 and will produce nascent hydrogen. But again, we know through inert per effect that tin in +2 oxidation state is more stable, because for p block element down the group, stability of group oxidation state -2 increases. I hope we remember that from inert per effect. So you tell me, Sn +2 is more stable or +4 is more stable? +2. So whether the reaction will be going in forward direction to a large extent? No, it will be going to forward direction, but to a very small extent. So the number of nascent hydrogen that will be produced will also be not that high, it will be less. So again here also this stannous chloride will do what? It will do partial reduction. Rather, if you use Sn in presence of HCl, then it will tremendously produce SnCl2, and then you have complete reduction. So complete reduction of this nitrile will give you 1 degree amine, but I have to do partial reduction. Therefore Stephen told us, and therefore now we know that partial reduction will take place. So what will partial reduction do? Only break 1 pi bond, not 2 pi bonds. So 1 pi bond broken, hydrogen added, and the intermediate is then termed as an imine. Now we know this imine has polarity, carbon being positive, nitrogen being negative. When introduced by hydrolysis, the lone pair of electron, that is excess of electron, will attack the plus. So this carbon will get the oxygen from the water, and therefore this bond will be broken. This carbon will be getting 2 OH. One carbon having 2 OH is unstable. It will dehydrate, resulting into the formation of corresponding aldehyde. The H plus of water will be going to this nitrogen, and it will be released in the form of ammonia, a very classic mechanism also. It is also there in NCERT. So although if you do not know the mechanism, still for your mains level questions and for as a matter of fact for your advanced question also, yes, for some questions you should know the basic. So I have given you the basic, but let us apply whatever we have learned in the question. Now it is saying we have what? We have again pent 3-ene. So I have a 5 carbon reactant. So this is a 5 carbon, I'm sorry, this is a 5 carbon reactant. At first carbon I am having an aldehyde. So okay, let me number it also for case of simplicity. 1 2 3 4 5. So this first carbon has become an aldehyde, and between third and fourth carbon I should have a double bond, because it is saying 3-ene. 3 means 3 4 should have a double bond. Now this is reacted with SnCl2. Now why I have deliberately taken unsaturation? Because Lindlas catalyst reacts with alkyne to produce alkene. This this stiffened reduction do not react with alkene also, do not react with alkyne also. You should remember this. So you use this. Obviously it will not react with alkene, and it will only react with the, okay, it is saying enal. Okay, so it should not be enal, because if you want to do stiffened reduction, what you should have a nitrile. So rather, I'm sorry, you should have, instead of this enal, this should be triple bonded N. This should be a triple bonded N. That means rather it should be pent 3-ene 1 nitrile. I beg your pardon, this is a wrong example. It should be this, because who reacts with stiffened reduction? Nitriles. So what I should have a nitrile. So this nitrile, once introduced with SnCl2, forms an imine, and post hydrolysis you do not have to do the complete mechanism, just make the 5 carbon chain, 3 4 5. Where is the double bond? Double bond is between third and fourth carbon, so as it is, and this triple bonded N will become a corresponding aldehyde, and ammonia will be released. Although you should not know this also, because for your mains level of questions you should just know what is the specific action of the reagent. So I hope we know what is the action of stannous chloride. Now the same action which is done by stiffened reduction is also done by DIBAL-H. Now what is DIBAL-H? DIBAL-H is di. D stands for di, I stands for isobutyl. Now what is an iso group? First carbon, second carbon having a methyl branch and a free valency. I hope you can see that isobutyl group. This is an isobutyl. Okay, so in order to make it an isobutyl group, I should have one more carbon. So over here, let me correct this also, because it is saying isobutyl. So what is an iso group? Iso is definitely first carbon, second carbon and a methyl branch, but this should have one more carbon. For example, let me take a marker over here. Okay, so this is the first carbon, CH2C. Now just look over here, what I said, first carbon, second carbon and a methyl branch. But if it had a free valency, it was isopropyl group, but we are using isobutyl, so you should add one more carbon, and now the total carbons are 4. So isobutyl. What is iso group? The second carbon should have a methyl branch, and if you want the bute, so add one more carbon. If you want pent, add one more carbon. For example, I wanted a bute over here, so first carbon, second carbon, a methyl branch, then one more carbon, because if it would have been like this, it is isopropyl. Now this is isobutyl. Now this is your complete 2 as in di isobutyl group with an aluminium having hydride. So this becomes di-isobutyl aluminum hydride. Now it is also again a partial reducing agent. Partial reducing agent will do what? Will reduce nitrile, and nitrile once reduced forms imine, and post hydrolysis it will give you the corresponding aldehyde. Like for example, what I have over here, hept as in 7 carbons, so 1 2 3 4 5 6 and 7. Let me number this for you. So this is carbon number 1 2 3 4 5 6 and 7. At the second carbon I have double bond, so this is 2-ene. At fifth carbon, so 5th 6 has an ine, and first carbon is having a nitrile. Okay sir, so this is my nitrile. Now what stiffened reduction do? The same is done by DIBAL-H. So if I react with DIBAL-H followed by hydrolysis, you do not have to worry, you do not have to think about anything. Just take all these number of carbons. Why? Because I'll just change its color also. Why? Because it is indifferent. It is indifferent that whether you have alkene or alkyne, it will not disturb any of the unsaturation and will only react with nitrile and give you the corresponding carbonyl compound. So what will be the name of the product? So again, obviously name is still clear to us. So this is hept 2-ene, 5-ine, and at the first carbon I have a functional group called aldehyde. So vowels has to be strike down, so because it's a vowel, so E is strike down. Because it's a Y, so E is strike down. I hope the IUPAC is also clear to us. Now moving forward, moving to a reactant that distinguishes between DIBAL-H and your SnCl2 and HCl, that is your stiffened reduction. Now DIBAL-H also reduces esters to corresponding aldehyde. Now I have an ester over here. I have O8, that means O8 means I have carbonyl group and an alkoxy group attached to this carbonyl group. That means it's an ester. Now what's the alkyl group? It is ethyl, so this is C2H5. Now what is the number of carbon I am having in main chain? 10 carbon chain. So this being the first carbon, so rather I should have 8 methyl groups and end it with a CH3. So this is a 10 carbon chain. So decane, at first carbon I have O8, that means it is an ester and an alkyl group. Now SnCl2 do not have a capacity to reduce esters, but DIBAL-H can also reduce this ester and can successfully produce, let's say I have this CH3, this CH2, how many? 8, and this carbonyl group gets reduced using DIBAL-H, and obviously this ethanol will be created as a byproduct. So DIBAL-H also reduces ester. SnCl2 specifically do not have much percentage yield, so as per NCERT we say DIBAL-H also reduces ester to corresponding carbonyl compound, and preferably it is always an aldehyde. Now coming to the last method of preparation, although there will be many sub reactions of the sort where we can produce aldehydes using aromatic hydrocarbons. Talking about the first type of reaction, which is partial reduction of toluene. Now we should definitely know this. I'm telling you this again, that if benzene is connected with the carbon, that methyl group can be easily oxidized using a strong oxidizing agent to form the corresponding carboxylic acid. We'll be studying that in the preparation of carboxylic acids. But if we have partial oxidation, then before carboxylic acid we can stop at the aldehyde stage. How to do that? If we make a complex, so in order to make a complex that will restrict the alkyl group to form corresponding aldehyde, so such reagents are also loved by JEE and are already there in NCERT. Major two oxidizing agent which will do this partial oxidation are chromyl chloride and chromic oxide. Now chromyl chloride is used independently in presence of a non-polar solvent like CS2. So when you use a chromyl chloride, you create an intermediate chromium complex. Now it is toluene, that means it is methyl benzene. Now this carbon, the terminal carbon, the last carbon, this carbon is 2 bonds, a geminal complex is formed. What is a geminal compound? If one carbon will be having 2 free valencies, and to that carbon, if we form this, although you can forget this complex, that what is this complex, but you should remember in your mind that the last carbon, so what is the last carbon which can have 2 different valencies? Sir, this methyl carbon. So it will form a complex. Now this complex will not allow this carbon to get oxidized to a larger extent. So if we do hydrolysis, reaction will be the carbon will be oxidized till this level only, and post that the bond will be broken by hydrolysis. So this will be removed in form of OH. I'll be having H plus over here. The carbon having 2 OH will undergo dehydration and will result in the formation of the aromatic aldehyde. This is a very famous naming reaction, also known as Itard reaction. So use of chromyl chloride, this chromyl chloride, it is also a test. If you have a salt of chlorine, the chlorine salt can be tested using the production of chromyl chloride vapors. So this chromyl chloride can also be used to prepare aromatic aldehyde. Similarly, if we use chromic oxide in presence of acetic anhydride, then at around 0 to 10 degrees Celsius, they also form an intermediate compound. Now, this intermediate compound is benzylidene diacetate. Now, remember that iodine is a general naming given to the geminal position of a carbon, but here I have formed a diacetate instead of a chromium complex. You can forget this intermediate. Ultimately, after hydrolysis, what we are doing, after hydrolysis, this carbon is turning into a aldehyde, becoming benzaldehyde. But I mean, most of the students commit this mistake. Like, for example, you have methyl benzene, you have alkyl benzene. That means, let's say, benzene is connected with this CH2 and then a CH3. Now you tell me who has the capability, who is the terminal carbon over here? So this one is the terminal carbon. I hope you can see that most students make this mistake. This is a terminal carbon, and whatever reactions we have seen is done on the last carbon that is attached with the benzene. So what is the last carbon attached with the benzene? This one. So who will form that intermediate complex? This one. So who will entertain the hydrolysis? This guy. That means both these reaction will produce what? Sir, benzene ring will remain as it is. This is CH2 and that was the last carbon. Let me change its color. This CH now will, after hydrolysis, it will be receiving oxygen from the water, and this will be your product. So what will be the IUPAC name of this product? This is carbon number 1, carbon number 2. So this is 2-phenyl. Then I have 2 carbon chains, so ethane, and first carbon is an aldehyde. So this becomes your product. Moving forward. So if we wish to add the carbonyl carbon and produce an aldehyde by introducing the carbonyl carbon to the benzene ring, then we can do that also using Gattermann-Koch reaction, or simply because we are producing aldehyde, so Gattermann-Koch aldehyde synthesis. Now how to do it? We use a mixture of CO, carbon monoxide, and HCl in the presence of anhydrous AlCl3 or cuprous chloride as catalyst. You will directly be adding the aldehyde group on the benzene. Sir, how it is happening? Although for mains level of question you should not know this, but for good question you should know the mechanism. The first point of the mechanism which I am mentioning is actually mixture of CO and HCl at a temperature of around 200 degrees Celsius at a pressure of around 6 to 12 atmospheric pressure. They produce this simplest acid chloride, which is methanoyl chloride, and normally one carbon acid is known as formic acid, so this is simply formyl chloride. Now sir, if I have a formyl chloride as an acid chloride in presence of anhydrous AlCl3, that we already know, this is Friedel-Crafts acylation. So actually we are doing this Friedel-Crafts acylation only, but sir, show me the electrophile. I cannot see the electrophile if I see a mixture of CO and HCl. That's why this mechanism is important for good questions. So let's say this is CO, carbon having a negative charge, so it will be protonated by the H plus given by the HCl. Now as soon as this hydrogen gives electron to the hydrogen, oxygen being positively charged will demand electron and will create a positivity at the carbon. Now bingo, there you see the electrophile. Now this electrophile will be doing what? Will be doing electrophilic substitution to what? To the benzene ring and getting substituted. Now why I am telling you all this? Because for a good question, let us say I have a question like this. I have a substituted benzene now and it is anisole. Now we know this mixture of CO and HCl is going to produce nothing but this CH with a double bonded oxygen, and this carbon is going to act as an electrophile. So now you tell me where this electrophile will be directed. Sir, I hope everybody knows that this oxygen is an alkoxide group which will create plus R. That means it is an electron donating group. It will enrich the electron density at ortho and para position, but ortho will be having steric hindrance. So relatively, what will become the major product? The para isomer. So this anisole is having OCH3 over here, and it will be directing the mixture of CONHCl in the form of aldehyde at the para position. So what will be your product? Because now aldehyde is a senior functional group, so that will be acting as a branch. So our IUPAC name will be at 4th position. I'm having this methoxy group, so this is 4-methoxy, and obviously benzene with CHO is known as benzaldehyde. So I hope it is clear that now I am not using the exact JEE questions, because JEE questions, if you find one, you will find 10 of the questions asking the same thing. But I am consolidating everything so that we be time effective also, and we take maximum result out of this time that we are investing in this one shot. Now, moving to the last method of preparation of aldehydes from hydrocarbons. Now, technically, this is a method which we have already done in the chapter of alkyl and aryl halides. How, sir? Let's say I have this substituted benzene, toluene, alkyl substituted benzene. Remember, chlorination or bromination in presence of sunlight used to do what, sir? It used to do allylic substitution. So if you are supposed to have an allylic substituted carbon, then obviously this toluene will be as it is. But if I am doing it 2 times, so the first time 1Cl will be substituted. If I do this allylic substitution, that is chlorination or bromination in presence of sunlight, then again allylic substitution can take place. So you can limit the number of substitution reactant is getting reactant is subjected to. Now I can even have 3 times of chlorination, but that will be requiring more amount of this reactant. So for your questions, essentially you can be specific that how many times you are doing it. Like for example, over here I'm doing this allylic substitution 2 times. So this chlorine has this I have got a geminal dichloride. Now this geminal dichloride, when subjected to hydrolysis, now sir, we again know this is classic SN1 mechanism. This chlorine will be gone and OH will be introduced. One carbon having 2 OH. I hope we have done this also a lot of time. One carbon having 2 OH. So definitely that's why we have used high temperature also, because this high temperature will allow the dehydration, and once dehydration has taken place, what product you are going to get? This benzene, this CH, and with a double bonded oxygen. So this is again your benzaldehyde, but this formation of benzaldehyde we already know through the chapter of alkyl and aryl halide. Moving directly to the preparation of ketones. Now, how we have prepared only aldehydes? Basically using 3 methods. First was using acid chloride, the Rosenmann reduction. Second one was Stephan reduction of nitriles, and the third one was hydrocarbon. So similarly, if you just want to create only ketones, then they can also be produced using the same 3 reagents. Like the first one is using acid halides. But if you want to create aldehydes only using acid halides, we have done the reduction using Rosenmann reduction. Here we use dialkyl cadmium. Now what is dialkyl cadmium? R2CD. So whatever alkyl group we introduce along with this metal, that will be substituting this chlorine, and this chlorine is gone. On one side you are having any alkyl or aryl group, on the other side the alkyl group is introduced, and therefore what product you get is only a ketone. Now some of the times NCERT even ask you that how can you prepare this dialkyl cadmium. So this dialkyl cadmium is also produced by none other than our famous Grignard reagent. So let's say if Grignard reagent has any alkyl or aryl group, if it reacts with cadmium chloride, it actually results in the formation of dialkyl cadmium. So this dialkyl cadmium you can produce using Grignard reagent. So for example, let us practice a question on the basis of what we have learned. So let's say I have an acid chloride, ethanoyl chloride. So eth has in 2 carbons, And what acyl halide we generally use? Chlorides, because the chlorine is a very good leaving group as well. So this leaving group will leave. Now here I am not supplied with the dialkyl cadmium, I am supplied with the reactant of dialkyl cadmium. So what is the Grignard reagent I am using? Phenyl magnesium bromide. So when this reacts with CdCl2, obviously now I know that this is going to produce phenyl whole twice Cd, as in diphenyl cadmium. Now because there is a metal, so you can either have alkyl or aryl halide. So whatever it may be, whatever alkyl group I have, this group will directly be getting substituted and this chlorine will be getting removed. So our product will be this CH3 is as it is, this carbonyl group is as it is, and we are just now being introduced by this phenyl group from the Grignard reagent, or we can also say from the diphenyl cadmium. So what will be your product? The benzene containing CH3. I hope we know the general name of this ketone. This is classic acetophenone. So this is the first method by which you can prepare only ketones. Moving to the next method, again in aldehydes also we have used reactant of nitriles in stiffened reduction. Again we use nitriles, but if we want to use nitrile and make a ketone, then again you have to use Grignard reagent. That's why Grignard reagent is very simple, also very easy also to remember. Again this alkyl or aryl group attached with the Grignard reagent will act as an electron rich species, because magnesium being a metal will always be plus, forcing carbon to be minus. So any type of carbon, aliphatic or aromatic, will take the electron and this minus will attack the carbon of the triple bonded nitrogen, resulting into the formation of this intermediate. Remember, Grignard reagent only functions in dry ether. There should be no species that has a capability to give hydrogen. So leave water, I should have no species that can give H plus, even slightest of H plus. That's why we do this reaction in dry ether. So as this intermediate is produced, now we do hydrolysis. This bond will be broken. The positivity of carbon will be given minus of water, so this carbon will be getting 2OH. After dehydration you get your corresponding ketone. So this will again, actually if you just see this, both the reactions are nothing but reactions of Grignard reagent. Grignard reagent with both, Grignard reagent with nitriles and Grignard reagent with acid chlorides. And at last, from hydrocarbons, although in case of aldehydes we had 3 or maybe 4 reactions which were giving you only aldehydes, but for ketones again it is quite simple, because we have done this in the chapter of hydrocarbon. If I have benzene, then we can do Friedel-Crafts acylation. You can use any acid chloride, it can be aliphatic, it can be aromatic, in presence of anhydrous AlCl3, and this chlorine will be gone, creating a positivity. So acyl carbocation will be created and will be getting substituted. So this way also, what product you will be getting? You will be only getting ketone. Moving forward, so moving further, let us quickly attempt some JEE mains questions and see that whether we have done something or not. So this is a 2024 question, a simple NCERT based question. Benzene reacting with mixture of CO and HCl, we know it is formylation and it will give rise to benzaldehyde. So what reaction it is? Just you see the reaction and move forward. So it is Gattermann-Koch reaction, we have already seen. Now oxidation of toluene to benzaldehyde can be easily carried out. Toluene to benzaldehyde, remember those Etard reaction and chromium complex formation. So CrO3 in acidic medium is a strong oxidizing agent. And what does strong oxidizing agent do? It converts toluene into corresponding carboxylic acid. So it will rather do complete oxidation, so not an answer. Yes, in acetic anhydride followed by hydrolysis, yes, this definitely going to give mild oxidation. So what will be a product? Acetaldehyde. So definitely 2 is my answer. But let us explore the options. KMnO4 again is a strong oxidizing agent, so it will again do complete oxidation. So toluene converts into benzoic acid, so not an answer. And CO and HCl in presence of anhydrous AlCl3. Now, because I have a substituted benzene which is toluene, which is plus hyperconjugation, so it will also direct the incoming electrophile. Electrophile in this case will be aldehyde at ortho and para position, where para will be the major product. So instead, in this case, I'll get a para CH3 substituted benzaldehyde, not only benzaldehyde. So our answer will be definitely option 2, but I'm discussing everything about the question. Again, this is also 2024 question. Acid chloride forming aldehyde, classic naming reaction, Rosenman reduction, because this is poisoned palladium. Moving to the next question. The next question is again the NCERT. If I have chlorination, then allylic substitution takes place. So maybe 1 time, 2 time, 3 time, because it is not mentioned. But post hydrolysis and at temperature of 100 degrees Celsius, dehydration takes place. So let us look at the option. It is saying it is aldehyde, aldehyde, aldehyde and acid. So if yes, we can form acid also, but for acid I need 3 chlorines. So if you are giving me 2 chlorines, that means you can only form an aldehyde. So direct NCERT questions are asked, as I have already discussed. Now this is again Friedel-Crafts Acylation, where this will be our electrophile. This electrophile will be directly attacked by the benzene ring, leading to the formation of what? One phenyl group, then a carbonyl group and another phenyl group. That means it is nothing but diphenyl ketone. Moving to the next question. Now these all are JEE mains question, mind you. So if you are if you are very much familiar with the theory, then these questions are very much doable. Now coming to the next question. Now about this question, obviously one thing we know, that this is delta minus, the electron rich nucleophile. It will attack the carbon, and post hydrolysis nitriles gives you corresponding ketone. So obviously this alkyl group will be added. So I have this benzene. This C has just now been introduced by this methyl of the Grignard reagent, and post hydrolysis it will turn into a ketone. That means it's an acetophenone. But although this is a common sense, we'll be seeing this common sense in later in this chapter as a reaction of esters. But obviously it is our common sense as well, that what is it, sir? This is C double bonded O with OCH3. You tell me, if this CH3 minus was attacking the positivity of triple bonded carbon, can't it attack this positivity, sir? Yes, definitely it will attack. So this CH3 minus will also attack first this ester, as a result of which first the alkoxide group, the Ro minus group will be leaving. So first CH3 will be entering to convert this ester into a ketone. And once this ketone has been formed, now we very well know that because CH3 MgBr is in excess. So this we will be seeing in the chemical reactions of ketone. But now because this is a common sense, so I'm discussing over here also, that once one CH3 minus has attacked, another CH3 minus can further attack. So if another CH3 minus attacks, then obviously over here I have got a ketone, but over here this is a carbon. One CH3 has been introduced and substituted OCH3. Another CH3 will also be introduced. It will convert this O into O minus, and post hydrolysis this O minus will also get H plus from the medium. So that means above nitrile forms a ketone. It will not further react. Nitrile forms a ketone. That means no, I do not have a ketone. Yes, it is forming a ketone. No, I'm not having a ketone. Yes, it is forming a ketone. But the para position carbon ester, first it will convert into a ketone, and the ketone will further react because Grignard reagent is in excess and will form the corresponding alcohol. Let us check the answer. Yes, it is option number 2, although we'll be seeing this in the reactions of carbonyl compounds again, because ketones or aldehydes, as a matter of fact, when treated with excess of Grignard reagent forms alcohol, which we now, why I am discussing this, sir, reactions of ketones are still pending, because we have already seen in the chapter of alcohols. So see, organic chemistry is all related. Moving to the next question. Now again, this is some people might say this is a question from hydrocarbon. You see the double bond, you break the double bond on and you add, because this is a reductive ozonolysis, so you add double bond O. So this is CH3, C, this is H, double bonded O. Why I'm not making the other product? Because that will also be the same. So this is nothing but acetaldehyde, and how many oxygen this acetaldehyde is having? Only 1. So the total number of oxygen present per molecule of the product. Now this is one molecule of the product. I'll have one more molecule of the product, but per molecule of the product, how many oxygen it is having? Just 1. So 1 will be your answers. Now these all are direct JEE mains questions. Moving forward. Now, again, in NCERT logic, the chromium intermediates formed and post hydrolysis, what is giving you? Sir, benzaldehyde. Sir, we have already seen one is ITAD reaction, one is use of chromic oxide. So this with acetic anhydride, what do we use? We use CrO3, which is chromic oxide, and with carbon disulfide, what we use chromyl chloride, CrO2Cl2. So B is CrO2Cl2. Obviously option 2 is right. So I mean, you do not have to move your pen if you have NCERT in your head. So moving to the next question. Now, with DIBAL-H followed by hydrolysis, nitriles and ester both can form corresponding aldehyde. So this nitrile will form CHO. So I can see a CHO, good. I can see no, it is imine. Intermediate is imine. For after that, ultimately after hydrolysis, you report a aldehyde. So this is an aldehyde, I'm comfortable. This is an aldehyde, I'm comfortable. So except option 2, with nitrile, aldehyde is getting formed. Now, because we also know ester also undergoes reduction with DIBAL-H. So how come the reduction must be taking place? Sir, it is also quite easy. How? This carbon will be getting hydrogen and this oxygen will also be getting hydrogen. So here you'll get your corresponding aldehyde, and that will be your corresponding alcohol, because this is just a reducing agent which will add hydrogen. So I need an alcohol just at ortho with respect to this CN. So with respect to CN, no, the ring must be opening. So this is wrong. The ring is opening and I'm getting OH over here. Good. This is first carbon and second carbon. This is first carbon and second carbon. Yes, this is right. Let me see this one. Obviously, this the ester must be opening and forming aldehyde and corresponding alcohol. So that is also wrong. Now, such questions may appear difficult to you, but once you know NCERT, questions will be quite doable. Now, moving forward. Now, this is reacting with HBr. Now, we have read the chapter of alcohol phenol ether. So, mixing alcohol phenol ether, aldehyde ketone. Now, this is how mixed packet question comes. So, first of all, the lone pair on ether will attack the H plus and they will get protonated. Once this oxygen gets protonated, this bond can't be broken. Why? Because it is having partial double bond character, because lone pair ion resonance with the benzene ring. So therefore we know that this bond will be forced to be broken, and once this bond is broken, I have a benzene over here. This aromatic ether is still there with an hydrogen. That hydrogen has been obviously given by HBr, and just now we have been introduced this carbon, this CH, which is having this methyl group. So let me draw this methyl group over here, and just now it has gained a carbocation. Why? Because oxygen will withdraw the electron and this OH will be formed, and this plus will ultimately be introduced with, because post H plus, who is going to attack? HBr. So this will be attached with Br. Now I'm doing one more thing over here over here only. What? Question is saying you are having excess of HBr. That means H plus and Br minus will attack again. Sir, where? Again we see there is excess of electron. So where you will find stable carbocation? Sir, let's say if I have a positivity over here, that means hydrogen must have attacked over here. That means positivity is formed over here. Then this is a resonance stabilized carbocation. Why? Because it is a benzylic carbocation being stabilized by the resonance of benzene ring. So obviously this plus, ultimately this plus will be more stable, and hence this should get the Br. I hope we are clear with what is our product A. Now we can clearly see our product A. Post that, what we are doing? Reaction with alcoholic KOH. Now we definitely know alcoholic KOH will form an alkene. But what alkene is formed? Sir, more stable product is formed. Now if I remove this bromine and this hydrogen, then I will get a conjugated double bond over here, because ring pi sigma pi and conjugated alkene is resonance stabilized, so obviously it will be formed. And after that, if this bromine and one of the hydrogen of that carbon is gone, then I can have a double bond over here also, so it will have a conjugated stabilization. So rather, for option for the product B, I'm having OH over here, no worries, but this is first carbon, then this is first carbon, second carbon, third carbon and fourth carbon. So first, second, third and fourth. And what type of alkene I should make? I should make a conjugated alkene. Why? Because the ring will be in conjugation with pi sigma pi, and obviously by Sidzeff rule, what alkene we form? We form the most stable alkene, whatever you call it, Sidzeff or Hoffman, always more stable product is formed. So this will be your Bombay. Now what are we doing with this Bombay? Ozonolysis. What ozonolysis? Reductive ozonolysis. So obviously we know that this bond will be broken. I'll get double bond O both the sides. This bond will also be broken, but in the option you can clearly see you are not asked about this. Although we definitely know we'll have a double bond over here also, double bond over here. So this will be 2 carbon aldehyde. What about this one? So this at that I mean over this side, because this has got a double bond, so this will be CH2. So this CH2 will also have double bond O. So this will be product 1, this will be product 2, but none of the option is talking about this product. It is actually talking about the benzene substituted product. So what will be the benzene substituted product post ozonolysis? The OH will remain as it is. I have a carbon over here. This carbon has been just now introduced by a double bond, and it will be an aldehyde because tetravalency says carbon should have an hydrogen. So that means that should be a product. Let us see if I have a product over there. Yes, OH and then CHO. So option 1, let us check the option. Yeah. I hope we are clear with this. So option 1 is your answer, because this bromine can't be here. This is an acid, so it can't be true. This is bromine, so can't be true. So option 1 is your right answer. Now this is a good time consuming question, but with such questions you gain confidence of recollecting all the organic and bringing them together. Now moving to the next question. Now the next question is again a JEE mains question using the knowledge of DIBAL-H followed by acidification. So we know it's an ester, so ester should form what? Ester should form corresponding aldehyde, and DIBAL-H, Stephan reduction, they do not react with unsaturation. So if at all I have a double bond or a triple bond, they will be remained inert and only ester will be reacting. So how you are supposed to form the product? Whatever carbonyl compound you have, make an H, and the oxygen will have again an H, so alcohol and corresponding aldehyde. So let us check. Benzene should have a cyclic ring. Yes, benzene should have a cyclic ring. Yes, pi should be there. The pi is getting reacted, so cancelling this option. Pi is there, but I should get an alcohol. Yes, pi is there. I'm getting an alcohol also. I'm getting aldehyde also. So option 4. I mean, you just have to open your eyes and answer will be visible to you once you know NCRT. Now The next question says it is a statement based question. Such questions have been increased in January attempt to a large extent, but still practicing it. Statement 1 says on heating with potassium bisulfate, glycerol is dehydrated. Now, what is glycerol? Now, this is a good question. Although somebody will say this is a question from alcohol, but because we have just now been introduced with some of the preparations of aldehydes and ketones, so we can use the common sense of alcohol and use in such questions. For example, what is glycerol? Sir, we definitely know glycerol is a 3-carbon chain, each carbon having OH. The general name is glycerol. Now, post dehydration with potassium bisulfate, we definitely know how we should predict dehydration. First of all, protonate OH and remove it so that a carbocation is formed. So, I mean, you can think of wherever producing the carbocation, but I feel obviously the degree of carbocation will also be, I mean, rather sufficient enough. So this will be a carbocation. Post formation of this OH has been removed in form of water. This carbocation, obviously you will be having hydrogens also over here. So you will take electron of hydrogen. So after removal of that minus H plus, you will be getting what? This carbon will be double bonded with the second carbon, third carbon is as it is, and this carbon is still having its OH. Now, what does you suggest after this? Sir, we suggest tautomerism. So post that, what we suggest? Tautomerism, because enol form is not stable. So tautomerize. So if it gets tautomerized, then hydrogen comes over here, double bond comes over here. So this is C double bonded O, single bonded. Now it just has become CH2. This will also be CH2 and an OH. One hydrogen will be here also. Now, after this, sir, still it is an alcohol. So still this OH can get protonated. So let us protonate this again. And once it gets protonated, it is removed in form of water or maybe OH, creating a carbocation over here. Once carbocation is formed, now this hydrogen, I mean one hydrogen will be here, one hydrogen will again be deprotonated to form a corresponding alkene. Let us draw the product. This is CH, this is double bond O, the CH2 will become CH and a double bonded CH2. Now, how many water of molecules we have dehydrated? 2. So post dehydration of those 2 water molecules, what have we formed? Sir, we have seen in the general name. This is nothing but acrolein. The general name is acrolein, and yes, acrolein is formed post dehydration of glycerol. So statement 1 is correct, and it is a property of acrolein. What is the property of acrolein? This acrolein rather is not fruity odor. It is actually a pungent smelling compound. Now it has an odor, but it is a pungent smelling compound. In fact, have a very suffocating odor. And yes, definitely, because it has an odor, therefore whenever it is formed, it can be used as a detection test. So yes, it can be used for detection of glycerol, but statement 2 is incorrect because its smell, its odor it's not fruity, it's rather very pungent. Therefore statement 1 is definitely correct, but statement 2 is incorrect. Moving forward, we have seen so many questions. After that, what we should do? The physical properties. But physical properties, sir, it is all basic. Once you increase the carbon chain, boiling point, melting point, all increases. If molar mass is comparable, then the molecule with stronger intermolecular force of attraction have a higher boiling point. So why writing and learning that theory again and again? Just practice question. So such questions are also asked in JEE. This is also a 2024 question based on physical property. The basic we already know. So this is an ether. It will have dipole-dipole attraction. It is alkane. It will have London dispersion force, so have weakest attraction. This is also, all 4 are having similar, almost approximately same molar mass. Therefore, I'm directly comparing their intermolecular forces of attraction. Now, this is a ketone, and the plus and minus, the polarity, because this alkyl group will also apply plus I. So actually, it is also dipole-dipole attraction, but the polarity of carbonyl group is not large. It is very, very large. So due to highly polar, this is quite high polar. This is highly polar. but again it will also have a dipole attraction, but the magnitude of dipole is quite significant as compared to ether. And yes, definitely, if you talk of alcohol, then alcohol are attracted via hydrogen bonding, which is the strongest intermolecular force of attraction, no doubt. So who will have highest boiling point? Sir, alcohol. That means D. Post that, C. So D should have the highest. Post that, you have C. So again, you have two options. Now after that, obviously the alkane will have the weakest, and ether will, although the polarity of ether is not also that large, but still, as if you compare it with the alkane, it is quite decent enough. So post that, I'll have A, and the least will be B. So option 2 will be your right answer. So directly learning physical properties with the proper question of JEE Mains. I hope it is clear. Moving to the next question. The next question again discusses about physical property, which we have already done in the chapter of hydrocarbons. I'm again repeating it. Now, if you say that as number of carbon chain increases, boiling point, melting point both increase. Yes, definitely correct. But what state of matter you melt? Sir, we melt a solid. And what solid has a relatively higher melting point? It not only depends upon the mass or the intermolecular forces. For a solid, melting point largely depends upon the crystal fitting, the packing of the complete structure of the molecule. So therefore, whenever we talk of melting points, certain more theoretical considerations has to be taken into account, which we have already seen in the chapter of alkanes. Just I'm revising so that those who have not seen can again feel this phenomena. So practically it is seen that whenever you have an even number of carbon containing species, so even number of carbon containing species tends to have a more symmetric packing. Again I'm repeating, even number of carbon chain tend to have more symmetrical packing. Sir, if we are more symmetrical, then we can be packed more closely. Therefore, melting point is relatively higher. Relatively higher as in, for example, as carbon chain increases. So whatever melting point, boiling point increases with carbon chain will definitely rise. But whenever you get an even carbon chain, the rise is significantly large. Although when it becomes odd, still the magnitude increases, but then the increment is not that large. Why? Because melting point of even number of carbon chain is significantly large as compared to the odd. Why? Because even number of carbon chains are symmetrically packed. Statement 1 is saying melting point of any functional group, as a matter of fact. So it is talking of carboxylic acids. So melting point of even of carboxylic acid with even number of carbon atoms are higher than odd. Yes, because of symmetric packing. So definitely this is true. And statement 2 says the solubility of monocarboxylic acid in water decreases. Now ultimately, why carboxylic acid are soluble in water? Because they have ability to form hydrogen bond with water. But who has the ability to form hydrogen bond? This C double bond O and this OH unit, not the carbon chain. So if you just increase the carbon chain, this soluble part is not going to change. And as carbon chain increases, the hydrophobic chain, the hydrophobic carbon chain is not entertained by water. Although carboxylic acids are soluble in water, but those who are having lesser number of carbon atoms. As the number of carbon atom increases, solubility will decrease. That means this is also correct. So both statements are correct. So option 1, let me check. Yeah, option 1 is your right answer. Moving forward. Now the next question is again physical properties. So next question says in the above, okay, I have two molecules. Now obviously this is quite easy. This is salicylic acid. So ortho substituted compound will have intramolecular hydrogen bonding. I'm sorry, ortho isomer will have intramolecular H bonding. So molecule will be involved in itself only. Para will rather have intermolecular hydrogen bonding. So intermolecular H bond will allow the para isomer to have more attraction among different molecules. So boiling point will be higher because it will be having much of boiling point. So obviously, it more boiling point because it will have a relatively higher polarity also, because who has a higher boiling point? Because this is interacting with another molecule. Why it is interacting? Because of the polarity, because of this minus plus, because of this minus plus. Sir, but it is para, it will get cancelled. No, it is not linearly arranged. So why you are thinking it will get cancelled? It will have some vector dipole moment which will be attracting another molecule. This will also be attracting another molecule. So rather, because it is more polar. So what is polarity? Polar is ionic nature. So that means ionic compounds are supposed to be form crystalline solids. So B being more ionic is more likely to have crystalline geometry. Obviously B has higher boiling point than A. This is also correct. B dissolves readily in water. Yes, because it can form hydrogen bond with water. That is involved in intramolecular hydrogen bonding. So it cannot form hydrogen bond with water. So obviously all the statements are correct. So what will be your correct answer? All statements are correct. Moving forward. Coming to the chemical properties of carbonyl compounds. Now the first and most important and easy also, the first property chemical reaction that is hugely shown by all the carbonyl compounds are nucleophilic addition. Now we definitely know, just like alkenes, the C double bond O is also having this pi cloud, and this pi cloud will also make this trigonal planar carbonyl group electron rich from upside also and downside also. But unlike alkene, which was electron rich, and to that alkene only the plus used to attack, as in it was primarily attacked by an electron loving species, electrophile. So alkenes rather gave electrophilic addition. But in case of carbonyl compounds, by seeing just this resonating structure, which is not very difficult also for us, that we know oxygen being more electronegative is very much eager to take these electrons. Therefore, a positivity is created on the carbonyl carbon, and this positivity is not very partial. This is a very high positivity that has been created on the carbonyl carbon, as a result of which, unlike alkene, now this positivity on carbon will make it electron deficient, and it is acting as electron deficient center. So who will try to attack this carbonyl compound? All the nucleophiles. So rather, carbonyl compounds are attacked by nucleophiles because of the positivity, high positivity on the carbonyl carbon. Now obviously we know this, but the most important thing is, let us say I have two carbonyl compounds, aldehydes and ketones. Now who has a higher reactivity towards nucleophile? Sir, ultimately nucleophile is coming. Why? Because nucleophile is interested in the positivity of carbon. So the first effect is electronic effect. More be the plus, more will be the attraction to the minus. If we have an aldehyde, then the delta positivity of the carbonyl carbon is reduced by the plus I effect of the alkyl group in aldehyde. But sir, in ketone, there will be presence of two alkyl groups. So that means whatever minimum, whatever delta positivity the carbonyl carbon of aldehyde carbon would be having will be larger. Why? Because this positivity is lesser neutralized by the plus I. Here the positivity is much neutralized by the electron displacement effect of the alkyl groups. So by the electronic effect also we can say that aldehydes have relatively more delta positivity, so nucleophile will be attracted more towards towards aldehyde. On the icing on the cake, I mean on the addition to this is the most dominant factor. But on the addition to this dominant factor, even when a nucleophile is trying to approach this carbon, it is also very much less hindered as compared to ketone. So ketone has on the basis of electronic factor also has lost the battle, and on the basis of steric factor also have lost the battle of attracting this nucleophile towards itself. Therefore, always remember this: aldehyde is not a bit; it is very reactive as compared to ketones. At first place, we take aldehyde and ketone as different functional group because of the same reason, that if you compare their tendency to do nucleophilic addition, aldehydes are very reactive towards nucleophilic addition as compared to ketones. Point number one. Now, if we compare aliphatic and aromatic carbonyl compound, whatever it may be, aldehyde or ketone, sir, we know if I have an aromatic aldehyde, then from GOC only we know that this carbonyl carbon act as a minus R group. That means this carbonyl carbons will withdraw the electron. What electron? The non-sigma electron. So because this is acting as minus R, therefore ring is acting as plus R. Because you are taking 100 rupees from me, so that means I am giving 100 rupees to you. So because carbonyl is minus R with respect to ring, so ring is plus R with respect to carbonyl group. That means this phenyl group is giving electron, and giving electron with what electron displacement effect? The strong plus R. Therefore, you tell me the positivity on this carbon is reduced because of electron donating nature, and we definitely know resonance is a dominating effect. So plus R will reduce the delta positivity to a much larger extent. So delta positivity will be very, very less, as compared to ultimately an alkyl group will only apply plus I, and inductive is much weaker than resonance. So you will have appreciable amount of delta positivity in case of aliphatic carbonyl compound, while that delta positivity will be drastically reduced in case of aromatic carbonyl compounds. So therefore, let us do the conclusion. What is the reactivity of these carbonyl compound towards nucleophilic addition? First is, obviously, aldehyde is more reactive than ketone, and if it is aliphatic, then any aliphatic, even it is aldehyde, even it is ketone. If you are aromatic, then you are less reactive. That means you are third. So our third position we are giving to aromatic aldehyde. So aliphatic ketone is better than aromatic aldehyde, but aromatic aldehyde is better than aromatic ketone. So I hope you remember this. Now, for some good questions, you should know this also, that obviously this carbonyl group is present in acid derivatives also, although we'll be seeing those acid derivatives, but NCERT do not discusses about acid derivatives a lot, but good questions of JEE does, although you can skip this also. Therefore I am just writing it as an extra point, that obviously this carbonyl compound will also be approached by nucleophile. So if you compare acid derivatives, who will show higher reactivity towards a nucleophile? Now for that, ultimately you should know that if this leaving group is leaving, whatever this leaving group is, if it is agreeing to leave, then which is a good leaving group? We know through alkyl halides, therefore I am revising it in a short span of time, that a weak base is always a good leaving group. So who is a weak base? Whose acid is strong? So HX being the strongest acid, the conjugate base, that is X minus, will be the weakest base, and weak base is a good leaving group. Therefore all the acid halides have highest reactivity towards nucleophilic addition. Any nucleophile can come and halogen will be left. That means if halogen is agreeing to leave, that means the acid halide are attracting nucleophile to a much larger extent. So who is most reactive towards nucleophilic addition? In fact, in this case it will be nucleophilic substitution, because once nucleophile will be coming, the leaving group will be leaving. So that's why I have not written addition, I have written reactivity towards a nucleophile. So who will be entertaining the nucleophile to the highest extent, acid halide, post that anhydride, post that ester, and last is amide. What you have to do to compare them? Strong acid has the weakest conjugate base. This is the strongest acid, follows by carboxylic acid, follows by alcohol, and amines will be weakest acid, hence their conjugate base will be strongest, and because base will be strong, so it will not be a good leaving group, because weak base is a good leaving group. I hope we are clear. Now that was an extra point, you can leave that also, but for the good questions you should know that. Coming to the examples. Sir, now we understood what is nucleophilic addition. Give us some examples. So the first and famous nucleophilic addition reaction shown by carbonyl compounds are addition of hydrogen cyanide, that is HCN. So about HCN is a weak acid, yes. Therefore, always when you use HCN with a carbonyl compound, you catalyze the reaction in presence of a base. Why? Because HCN itself will dissociate partially into H plus and Cn minus. But if you have a base, the strong base will take away this H plus and will bring the equilibrium to forward direction. So this is just application of common ion effect, the Lee-Chatelier principle that we know. Therefore, the addition of HCN always takes place it is always catalyzed in the presence of a strong base. Now, if I have a strong base, and then I had taken HCN, then I'll be having a lot of Cn minus ion available. So this cyanide ion will do what? Now sir, it is quite easy. We know this carbonyl carbon has delta positivity. So it will rather attack this trigonal planar carbon and it will form a tetrahedral intermediate. Post that, whatever proton is present in the medium through water, that H plus will be going to this O minus and you will get an alcohol, but for carbonyl compound, the product names are also very important. So this tetrahedral product has what? The carbon has got OH also and has got CN also. This class of product is known as cyanohydrin. I repeat, this class of product is known as cyanohydrin. One more thing, we'll be seeing this in nitrogen containing compounds, but I'm discussing over here only. What is the thing? Actually, whenever you have it is just an extra knowledge which I'm giving you at this point of time only, that whenever you have a nitrile group, this nitrile group can be easily hydrolyzed to form the corresponding carboxylic acid. For example, this C, the free valencies, whatever it will be, it will remain as it is. The alcohol will remain as it is. Now this carbon which you are seeing over here, this C, will post hydrolysis, first it will form an amide, and if you are hydrolyzing in a dilute acidic medium, then ultimately it is going to form carboxylic acid and ammonia gas will be, nitrogen will be released in form of ammonia. We'll be doing this properly in the chapter of in nitrogen containing compounds, but this hydrolysis of nitrile forms corresponding carboxylic acid, you should definitely know, because this is used in many of the conversions, even in many of the questions. So you should at least know this, although this is an extra point. Now, first addition is of HCN. HCN, whenever is added to a carbonyl compound, it forms the corresponding cyanohydrin. Now, what is the second addition? What is the second type of addition that is famous? Sir, of sodium bisulfite. What is sodium bisulfite? It is NaHSO3. I hope it is quite clear to you now. Because it's a salt, it can easily dissociate Na plus and bisulfate. The S minus will attack carbonyl carbon, thereby you will form this. But sir, O minus and Na plus, there will be a proton transfer because sulfonic acid is a stronger acid. So strong acid will give H plus and will force the weak acid to take hydrogen. So actually proton transfer will take place. Alcohol will take H plus and the stronger acid will form the salt. And actually whenever this salt is formed, it is an ionic compound. This ionic compound ionic compound forces the carbonyl compound to get precipitated. Precipitated as what? As a crystalline solid. So you can see that crystalline solid, and because you can see that crystalline solid, you can separate aldehydes and ketones. Sir, how can we separate? Let's say you have both aldehyde and ketone in a beaker. We definitely know that aldehyde are more reactive towards nucleophilic addition. So if we use limited amount of sodium bisulfite, all the aldehyde will get precipitated, leaving ketone in the solution. Now separate the mixture. in the channi, in the filter, you have separated out the crystals. The solid is having what? The solid is having aldehydes. In the filtrate solution, I have the ketone, so aldehyde ketone separated. But sir, aldehyde is not present in the form of aldehyde. It has formed an adduct. Do not worry. Why? Because whatever addition product you have obtained, the crystalline solid, you just make it, you just hydrolyze it, put water, excess of water in any medium, acidic medium or basic medium. The salt will undergo hydrolysis and it will give you the parent carbonyl compound. So you can actually again get that aldehyde and ketone by simply hydrolyzing that crystalline product. So for practical organic chemistry, it is very useful because this method is used for purification and separation of aldehydes and ketones. I hope it is clear to us now. Going to the third example of nucleophilic addition, which we have already done in the chapter of alcohol. So what? Addition of Grignard reagent. I hope you remember Grignard reagent is this R minus, this will be the nucleophile. Nucleophile will be attacking the carbonyl carbon of either aldehyde or ketone. Yes, Grignard reagent always do reaction in presence of dry ether. There should be no species that should have an ability to give hydrogen. I've already discussed that. This intermediate is formed and post hydrolysis you form the corresponding alcohol. I repeat, if you have hydrogen on both the sides, then it is formaldehyde. So formaldehyde will give you 1 degree alcohol because ultimately alkyl group is going to be added. So it will give 1 degree alcohol. But if you have any other aldehyde, it will already be having 1 alkyl group. So this alkyl group will rather produce 2 degree alcohol. And ketones actually forms 3 degree alcohol. So this is a conclusion which we have already made in the chapter of alcohols. Moving forward, the fourth reaction, the fourth example of nucleophilic addition reaction is addition of alcohols. Now, in the previous examples, the nucleophile was always charged. Sir, but alcohol is a covalent molecule. It is not charged. That's why if you want carbonyl compound to react with an alcohol, you have to first protonate the solution. For example, let's say if I'm using alcohol, then do not use alcohol independently. Catalyze the reaction by adding some HCl gas, because HCl gas will produce lot of H plus ions. These H plus ions will protonate the carbonyl oxygen and will create a complete positive charge on carbonyl carbon. Because nucleophile is not charged, so I'm making carbon a charged species. If kharbuja is not liked by you, then put churi on kharbuja. So because nucleophile was not having charge, so how I'm increasing the attraction towards them? By giving charge to this carbonyl carbon. Now this carbonyl carbon can now be attacked by this neutral nucleophile because oxygen is still having lone pair of electrons. Once the lone pair of electron is given, it will undergo deprotonation, and by the loss of this H plus, this OH and OR, this OH and OR as an hydroxy group is also present, alkoxy group is also present. This product is also generally termed as hemiacetal. So whatever aldehyde you have, it is specifically an aldehyde. I'm not talking of ketones over here. This is specifically an aldehyde. Let's say it is acetaldehyde, so we'll say it is hemiacetal of acetaldehyde. So this will become an hemiacetal. But sir, because still the medium has dry HCl and alcohol, then it will again be happening as in this OH will get protonated, water will be released. Once water will be released, another molecule of alcohol will react, and post deprotonation, it will again be dialkoxy. At the same carbon, I have 2 alkoxy group. That means it is a geminal dialkoxy compound, and it is generally named as acetal. Acetal is the general name of the geminal dialkoxy compound of aldehydes. Now, why I am saying aldehydes? Because in the previous cases I have said carbonyl compounds, because we have already seen that aldehyde has more reactivity towards nucleophilic addition. Here, the nucleophile is not even charged. So actually, the point is ketone being lesser reactive towards nucleophilic addition actually do not respond to monohydric alcohol. If you are an alcohol and you have only one OH, then ketone will not allow you to react. because ketone is less reactive. So rather, if you want an alcohol to react with a ketone, use polyhydric alcohol. Minimum you should have 2 OH. Like if you have ethylene glycol, then now. So again we have to do mechanism now. Now you can think of with a common sense. What is the common sense? This is the carbonyl oxygen. Let's say we are using 2 alcohol at the end of the day. For reaction, we are using 2 alcohol molecules. So this is one alcohol molecule, OR dash. This is another alcohol molecule, OR dash. So ultimately these 2 hydrogen and water and oxygen are getting removed. Ultimately you can clearly make the product without giving the mechanism. So ultimately you are doing dehydration. So if one alcohol is having 2 hydrogens, so why need 2 alcohol molecules? So this dabba will show you that water will be getting dehydrated, although the mechanism will be same, which the way I have explained, and ultimately you are going to form a ketal. But what ketal? Cyclic ketal, because ketones never react with monohydric alcohol. They only react with polyhydric alcohol. So moving forward, moving to the last example of nucleophilic addition, which is addition of ammonia and its derivatives. Now let us first see what is ammonia. Obviously we know ammonia is nitrogen having lone pair of electron, and those lone pair of electron will make nitrogen also electron rich, hence a nucleophile. So these lone pair of nitrogen will attack the carbonyl carbon and the bond shifting will take place. Now because nitrogen is electronegative, so it will snatch electron from a proton, so the H plus will be offered electron by the O minus, hence OH formed, and out of the 2 hydrogens, 1 hydrogen is gone, so we are left with NH and another derivative of Z. Although when this Z is hydrogen, this is simply ammonia. I hope it is quite clear to us. A very simple and a very probable ammonia derivatives questions are asked in your boards also, JEE mains also, advanced also. So a very important table I am directly taking from NCERT only, because this is very important now, and the best way to learn is through NCERT only. Now post this formation, sir, nucleophilic addition has taken place, but now it has been observed that with ammonia and its derivative, even if you heat it or whenever they are reacted, automatically the temperature attains to such a level that dehydration, as in elimination, is always followed by the preparation, by the addition. So actually some references also say that addition of ammonia and derivatives is also an example of addition elimination reaction, because in such cases addition is always supplemented, complemented by after addition reaction, it is always complemented by elimination of this water molecule. How, sir? Where can we find water? This H plus post protonation, it is released as this OH post protonation is released as water, and the plus is compensated by again hydrogen, the electron of this hydrogen. So post deprotonation you get a double bond between carbon and nitrogen. Now whatever be this last Z, if this last Z, nitrogen has 3 valencies, so 2 valencies are hydrogen, gone. The last valency, if it is hydrogen, then obviously this derivative is simply ammonia. So the product form will be this Z will be H. So the product that we have obtained, we have already seen this product. This product is generally termed as imine. Now general names are very, very important. I hope you are noting them. Now if this Z is an R, that means you have one degree amine. So 1 degree amine forms, instead of that H, you have an R, and this particular product is obviously known as a substituted imine. Some people even called it a Schiff's base. Now if that Z is an OH, then this is NH2OH, which is commonly known as hydroxylamine, and the product will be known as oxime. Now obviously the nitrogen lone pair will make this OH on one side, so geometrical isomerism of oximes are also possible if the 2 branches over here are different. We have even seen the nomenclature of oximes in our GOC logic, but I'm not overextending the chapter over here. All those who have been learning organic chemistry as a sequence, so the oximes they must have seen in GOC. Now, if that Z is again one more NH2, then this is NH2 bond NH2, which is definitely known as hydrazine. The product is known as hydrazone. Now, if this hydrazine is substituted by a phenyl group, then this is phenylhydrazine. The product looks like this and it is known as phenylhydrazone. Now, if I substitute the benzene of phenylhydrazine with nitro group at second and fourth position, that means it is 2,4-dinitrophenylhydrazine, also sometimes known as DNP. Why this DNP name is famous? Because the product, which is 2,4-dinitrophenylhydrazone, this product can be visually seen by your naked eyes. Why? Depending upon the concentration of DNP and carbonyl compound taken, all aldehydes and ketones react with DNP and forms either yellow or orange or red color precipitate solids, and those solids you can see. Therefore, this is a detection test for the presence of carbonyl compound. A very important practical organic chemistry logic also is used by this DNP test. Now, last is, if that Z is another NHCO NH2, then some people will say, why this NH2 will react, why this NH2 won't react. Again, that NH2 is only going to react because the lone pair of electrons on the nitrogen of this NH2 is obviously, I have already drawn it. It is in resonance with the carbonyl group, so they will be less available, while these lone pair will still be available, and hence the addition will still be initiated by the nitrogen lone pair of electron on nitrogen on this NH2, not the NH2 that is close to CO. Now, sir, if Z is this, then this reactant is termed as semi-carbazide, very important, and the product is known as semi-carbazone. So I have deliberately taken this table over here, because if you are seeing this table or you have not remembered and learned this table, then please make note of it and at least write it few times so that you can memorize it. Moving forward. Now, post nucleophilic addition reactions, we are moving to reduction reactions shown by obviously aldehydes and ketones. And these reactions, the first set of reaction we have already seen, because first is reduction to alcohols. We definitely know from the chapter of alcohols that aldehyde when reduced can form 1 degree alcohol. Ketones, any aliphatic or aromatic ketone when reduced forms corresponding 2 degree alcohol. Yes. Aldehyde forms 1 degree alcohol generally. Why I have written generally? Because if this aldehyde is a formaldehyde, then that formaldehyde when reduced forms a methyl alcohol, and methyl alcohol has no degree. So because just of the reason that formaldehyde on reduction forms methyl alcohol, which is not a 1 degree alcohol, that's why over here I have written generally. But yes, definitely ketone will always form a 2 degree alcohol. And what are the famous reducing agent? We already know them. Catalytic hydrogenation, they reduces practically all aldehydes and ketones. Lithium aluminum hydride and catalytic hydrogenation even reduces unsaturation, and most of the oxygen containing compounds are reduced because they are very strong reducing agent. Yes, but this sodium borohydride NaBH4 is a special selective reducing agent which only reduces aldehydes and ketones. A very important point for you to note, which we have already done. Now, already done where? In the chapter of alcohols. So coming to reduction to alkanes, now this also we have already been introduced in the chapter of hydrocarbon, but NCERT introduces over here. Although the reduction to alkanes involve 2 reactions, the first reaction is known as Clemmensen reduction and the second is known as Wolff-Kishner reduction, and they themselves has a very beautiful mechanism. But just for the question, for the mains question, I am skipping that mechanism because it is also not there in NCERT and it can only be used for a very good questions. So skipping that part, because knowing this much is more than sufficient. Hence, using the direct NCERT logic, whatever carbonyl compounds you have, they can be reduced to corresponding alkane. How? Clemenson says you use an alloy of zinc and mercury known as zinc amalgam. The reaction takes place in acidic medium, and this oxygen is ultimately removed in the form of water, and this reducing agent will add hydrogen to the carbonyl oxygen to the carbonyl carbon and convert directly into an alkane. Although through common sense only you can know, because it is happening in acidic medium. So apart from ketone, if you have an alcohol, then in acidic medium, then that alcohol can undergo dehydration and correspondingly form an alkene. But that will be a very good question. I mean, for the mains question per se, you can only know this logic which NCERT gives, followed by Wolff-Kishner reduction, which happens rather in basic medium. So if you have a carbonyl compound, first do the addition elimination via hydrazine. Hydrazine forms a hydrazone, the corresponding hydrazone when it is treated with a base, either NaOH or KOH, but the solvent should be a boiling solvent of ethylene glycol. So what happens is this nitrogen is removed in the form of nitrogen gas, and whatever carbonyl carbon we had, it directly converts into the corresponding hydrocarbon. A very, very important reaction, both of them. Yes, they have specific mechanism, but knowing this much is more than sufficient. This finishes the reduction reactions of carbonyl compounds. Coming to the oxidation, the third set of reactions. So the first set of reactions are nucleophilic addition. Second set of reactions are reduction of carbonyl compounds, and third set of reactions are oxidation. Sir, but oxidation we already know. I hope we have already done that in the preparations. When alcohols are treated with mild oxidizing agent, they produce carbonyl compounds, either aldehyde or ketone, depending upon they are 1 degree, 2 degree, 3 degree, cannot be oxidized. But when they are treated with strong oxidizing agent, 1 degree alcohol produces acid, 2 degree alcohol produces ketone, and 3 degree do not react. Although with dehydrogenation, 3 degree also undergoes dehydration. That we have already seen and done. Now, so why you are telling this again? Over there also I have told that the function of oxidizing agent is to break the C bond H of the carbonyl carbon and convert it into C bond OH. Oxidizing agent do not have a property of breaking the C bond C, but if you create some vigorous condition as in if you increase the temperature, increase the pressure, then that increased temperature and pressure will provide so much sufficient energy which will now have the capacity to break even the C bond C. And once C bond C is broken, then the strong oxidizing agent can perform their action. Once this C bond C is broken, now the strong oxidizing agent can convert whatever parts you will be having, those parts, the C bond H will now can be converted into C bond OH if you have a strong oxidizing agent. So ketones can be oxidized, and the oxidation is done, the statistical rule which has been validated and has been patented by a scientist called Popov. So it is known as Popov's rule. Now what is it? Some of the students learn it with the fact that carbonyl group goes with that alkyl group which is smaller. Sometimes it can help also for a mains level type of question, like for example over here, ultimately this C bond C is gonna break, but which C bond C breaks and what is the major product formed? There is a Ratane, there is a ratification rule also. Ratification rule says carbonyl group stays with that alkyl group which is smaller. So among the two carbonyl group which is smaller, this is smaller. So from where you will try to break the bond, so obviously you will try to break the bond from here, because carbonyl stays with that double bonded carbon with that alkyl group which is smaller. So ultimately this will create a 2 carbon alkane with this carbon having double bond O. So oxidizing agent will add 1 OH over here also, so it will become acetic acid. What about this one? This is first carbon will have OH. These 2H will also be replaced by OH because now strong oxidizing agent can function. So this will also turn into an acid. So 2 carbon acid from this side also and from this side also. So rather what should be your major product? Your major product from both the side will be CH3 CWH. Bingo, sir. So rectification rule is, I mean, it is quite easy to learn. That Popoff's rule says that double carbonyl group stays with the smaller alkyl group. But let me also give you the logic. Why? Because although for mains level type of question, 80% of the time your job will be done with carbonyl group stays with the smaller alkyl group. But actually why it is happening, like if I have a ketone over here and question is telling us that there is vigorous oxidation, so sir, this is also this is also, I mean, carbon 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 carbon. Yes, definitely it is a benzene ring, but still if you just look at the system that which is smaller, sir, then you will say that one is smaller. So maybe you are right or maybe you are wrong. Actually over here also what happens is ultimately there is no mechanism as such, because it is just a redox reaction. So nascent oxygen acts and corresponding product is formed, but I have a logic also in order to predict, in order to judge that what should be the major product. You just form the most stable of the keto, you form the enol form. Like for example, if I form an enol form of this compound, so this hydrogen can also be transferred. So if this hydrogen is transferred, so what will be the enol form that we will be thinking of? This hydrogen will be coming to this oxygen, so it becomes OH, and this single bond becomes double bond, and this becomes CH, then CH3. So this is the first possibility of the enol form. What should be the other possibilities? That this is also an alpha hydrogen, so tautomerism of this hydrogen can also take place with respect to this carbonyl group. So let us do the tautomerism. So it will be CH2 double bond C, single bond OH, then CH2 and CH3. Now actually whenever you are supposed to do oxidation of ketone, what oxidation? Vigorous oxidation. Think of its all the possible enol forms. Now, among these enol forms, which is more stable? Sir, think of the stability of alkene. Over here, you can see this alkene is not at all conjugated. And this alkene is much conjugated, substituted from this side also, from this side also. So relatively, I guess it is quite clear to you that this is the stable alkene. Now, we already know from the chapter of hydrocarbons, and over here also I have discussed the oxidation of alkenes. Oxidative ozonolysis of alkene or a reaction of alkene with a strong oxidizing agent do what? You see the double bond, you break the double bond, you add double bond O on both the sides and replace all H by OH. So a double bond will come in from this side, so this will become acetic acid. A double bond will come from this side, so this will become double bond O, H will become OH, so acetic acid. That will rather give you product, but those product will be minor product because that particular enol form, the alkene of the enol form, is less stable. So obviously we know we have came to the solution, the product, from logic also and from the rectification rule also, that alkyl group stays, the carbonyl group stays with that alkyl group which is smaller. Although I'm not writing it intentionally, because even I want you to learn, because such questions will come, that means they are good questions. So ultimately learn them by logic. So we'll try to make the enol form. Now over here also I can do this pink color hydrogen is also from carbonyl group, that is the alpha carbon, and this yellow color carbon is also the alpha carbon. Now if I have a double bond, by substituting the yellow carbon, obviously that double bond will be a conjugated system, because pi of the benzene ring, pi sigma pi will give you a conjugated alkene which will rather be more stable. So why bother writing that one? So what will be a stable enol form? Sir, this phenyl single bonded with this CH. Why CH? Because now it has turned into a double bond with this carbon, and this double bond has become OH. This hydrogen is the second hydrogen from there, so I have written single hydrogen over here. Remaining things are as it is. Now do its oxidative ozonolysis or reaction with strong oxidizing agent. So break this bond. So what are you left with? This is nothing but phenyl C double bond O, double bond breaks, double bond O is added, and all H are replaced by OH. That means this is nothing but benzoic acid from the left side. So this is the product from the left side of the reactant, and from the right side of the reactant we'll be having 3 carbons. So 1, 2 and 3 carbon. This is the third carbon, a double bond O from the oxidative ozonolysis, and already it is already OH. So this is benzoic acid, and 3 carbon acid is propanoic acid. So benzoic acid and propanoic acid will be the major product via vigorous oxidation of such a ketone. I hope we are quite clear with this. Moving to the next oxidizing agent. Now that was oxidation of ketones. Now for oxidation we know some basic things, but certain oxidizing agents also act as a test of carbonyl compound, where the next famous oxidizing agent is this Tollens reagent, which rather performs Tollens test. Now what is Tollens reagent? Tollens reagent is actually a freshly prepared solution of ammonical silver nitrate. Ammonical as in you should have excess of ammonia, and in presence of that ammonia you have silver nitrate. Now what is the inorganic chemistry behind it? If you have ammonia, if you have excess of ammonia solution, rather if you have limited ammonia solution with silver nitrate, then ultimately silver get precipitated in form of its oxides. This Ag2O solid is a precipitate. But if ammonia is in excess, if ammonium hydroxide is in excess, then this silver plus cation will form a soluble complex with coordination number 2, and the complex is formed with ammonia. Now this complex is the actual active species, is the actual active ion. So why we take a freshly prepared solution? Because this complex ion is not very stable. It has to be produced just in the runtime, and once it is produced in the runtime, therefore freshly prepared ammonical silver nitrate is taken. So this is your active Tollens reagent ion. Now what does it do? It does redox. Redox with what? It oxidizes aldehydes. Now remember, because we already know that aldehydes have a higher reactivity than ketones, so only aldehydes. Now this you have to remember, because it's an industrial and experimental fact that all type of aldehyde, whether aliphatic or aromatic, gets oxidized via this active Tollens reagent cation of silver plus, and because carbon of this carbonyl group is getting oxidized forming carboxylic acid, and who is getting reduced? Silver from +1 oxidation state is reduced to metallic silver. Now that metallic silver you can see, and because of the production of that metallic silver you see a silver mirror. So once you see a silver mirror, you are sure that whatever compound you have taken was an aldehyde. It can be aliphatic aldehyde, it can be aromatic aldehyde, sir. But why you are not reporting carboxylic acid? Because medium is basic, and in basic medium acid exists as its corresponding salt. So I hope we are clear. So why you have written those stoichiometric coefficient, although from redox reaction you can also know that stoichiometric coefficient, but because this is a very famous reaction, hence writing the balanced version from NCERT. I hope it is clear. This is nothing but Tollens test. Now for your JEE mains also, advanced loves it. But for your JEE mains also, you should know that only aldehydes are known to give positive Tollens test. No, some other compounds can also get oxidized, because ultimately it is a mild oxidizing agent which is oxidizing aldehydes, either aliphatic or aromatic, and oxidizing aldehydes is meaning it is not even mild, it is strong oxidation, because you are directly converting into an acid. So actually some more compounds can also be oxidized using Tollens reagent, and hence Tollens test will be positive for them also. So what are they? Learn them. A very beautiful fact I have designed for you. So at least learn this 3-4 times, because this is very important. Even in this JEE January attempt, a question from this side was asked. So even in JEE mains, advanced used to love it, now mains love it so much that even in one of the paper you are definitely going to get it. So which gives positive Tollens test? All of them. The first one being aliphatic and aromatic aldehyde, that we already know through NCERT. Second is Even formic acid respond to tolerance test. Even formic acid respond to tolerance test. That means silver mirror is produced. Formic acid and all the salts of formic acid. So HCOO minus, as in salts of formic acid and formic acid itself, they both give positive tolerance test. Coming to talking about esters of formic acid. So if I have this HCOO, then I can have any R dash. So esters of formic acid, so formate esters also give positive tolerance test. After that, hydrazine and ammonium hydroxide and their salt, they also give positive tolerance test. Next is alpha hydroxy compound. What is alpha hydroxy? Let's say I have a carbonyl compound. The carbon, sp3 carbon next to this carbonyl carbon is known as the alpha carbon. If that alpha carbon is having OH as an hydroxy group, then all the corresponding compound, now this carbonyl group is a necessity. This free valency can have anything. It can be ester, it can be acid, it can be ketone, it can be amide, it can be anything. I just need a strong electron withdrawing carbonyl group, and this carbonyl group should have an sp3 hybridized carbon which should have at least one OH. So all hydroxy alpha, all hydroxy compounds also give positive tolerance test. Along with that, in the reaction of carbonyl compounds with alcohol, we have already formed an hemiacetal. So all the hemiacetals, whatever be this free valency, it is a hemiacetal of aldehyde ketone, although we know that hemiacetal of aldehydes are only known in nature because ketones cannot form hemiacetal, they can only form cyclic ketal. I hope you remember that. So hemiacetals also give positive tolerance test. Then this diketo, generally, if you ask me, generally diketo do not give tolerance test, but one of the advanced paper I have asked it because it is also an experimental fact that yes, normally diketo do not give tolerance test, but on heating even the C bond C gets broken, and once it gets broken then the test can be given. So this diketo can also give positive tolerance test. That means you can get silver mirror. And last but not the least is terminal alkyne. Yes, with terminal alkyne you get a test, but actually you do not see a silver mirror because silver actually is not reduced from +1 to 0 with acetic acid. Actually with acetic acid, because not with acetic acid, with terminal alkynes, because terminal alkynes have acidic hydrogen, and that acidic hydrogen can react with the silver cation and forms a salt. So this silver salt of terminal alkyne actually gets precipitated and it do not create a silver mirror, rather it creates a white PPT, but ultimately you can see that white PPT. So tolerance reagent is actually reacting with terminal alkyne also, although not creating silver mirror but creating white PPT. That white PPT also you can see. Therefore some people say that terminal alkyne can also be detected using tolerance reagent, a very important fact. Now moving forward to the next mild oxidizing agent. This also is a mild oxidizing agent because it also oxidizes aldehydes. Yes, Felling reagent has a relatively lesser reactivity, therefore it only oxidizes aliphatic aldehyde, not aromatic. Point number one, it only oxidizes aliphatic aldehydes. Very important, because aliphatic and aromatic aldehyde can now be distinguished by Felling test. Both give positive tolerance test, aliphatic and aromatic, but only aliphatic gives positive Felling test. Now what is Felling reagent? It is constituted of two solutions, 50-50% of both. What is Felling solution A? It is aqueous solution of copper sulfate, in which you are actually given the copper +2 ion. Now copper +2 ion in water is generally not stable. So in order to hold it, you need Felling solution B, which is nothing but a basic solution of an alkaline solution of sodium potassium tartrate, the Rochelle salt. Now what is Rochelle salt? You have a 4-membered dicarboxylic acid, and in the second and third carbon you have the OH group. So what is its salt? So COOH replaced by Na plus, so sodium salt. COOH replaced by K salt, potassium salt, so K plus. So this is sodium potassium tartrate. And why it is used? Because it holds the copper plus 2 ion, because rather copper plus 2 ion is not stable in water. It directly undergoes reduction, but we want copper plus 2 to be there so that you can react with it. So this copper plus 2 ion is holded by this Rochelle salt. So Fehling solution A and Fehling solution B are taken. Ultimately, what active ion they give? Copper plus 2 ion in basic medium. Now this acts as an oxidizing agent, oxidizes only aliphatic aldehyde and produce corresponding carboxylic acid. But again, because medium is basic, so salt of carboxylic acid will be reported. If this is aldehydes are getting oxidized, then who is getting reduced? Copper is getting reduced from +2 state to +1 state, and copper in +1 state is not at all stable. In form of its oxide, it gets precipitated, and you can see this precipitate in the form of reddish brown PPT. So if you get a reddish brown PPT, that means the aldehyde that you are having in the solution is an aliphatic aldehyde, a very beautiful example of oxidation also. So we are doing oxidation of aldehyde also, and it is acting as a test also, as a distinction test also, because it is only given by aliphatic aldehyde. Now coming to the next oxidizing agent, and the last oxidizing agent that has a capacity to oxidize even the ketone, so rather we will say that it is also a vigorous condition. Now who creates a vigorous condition? Halogen in presence of base. Any halogen, X2, any X2 in presence of base act as a very strong, vigorous oxidizing agent. Why I'm again and again saying vigorous? Because it has a capacity to oxidize methyl ketones. Now what bond I'm going to break? This C bond C. Remember, breaking C bond C was not the function of an oxidizing agent, but if an oxidizing agent is breaking C bond C, that means it is rather a very strong oxidizing agent, because it itself has a capacity to break the C bond C. So it is definitely the vigorous condition. The vigorous condition can also be created using a mixture of X2 and NaOH. Sir, but you have not written X2, you have specifically written I2, because when you use I2 in NaOH, the product that is formed, you can see that product, and that yellow color product, because you can see the yellow PPT, so it also acts as a test. So the yellow PPT is only obtained when you use iodine in a base. So this halo form, out of all the halogen, iodo form becomes very famous, and therefore specifically we also term it as iodoform test. Now what is the test? This methyl group gets broken. Now specifically I'm not asking you to make the enol form, I'm specifically asking you to break the methyl group. Whatever carbonyl group you have, oxidize that, so you will form the corresponding acid, and this methyl group is precipitated in form of CHI3. Now CHI3, you can see it is a yellow PPT, so it is a test also. It is a strong oxidizing agent also. It is a strong oxidizing agent also under vigorous condition, because it is oxidizing a ketone. Now one point. This CH3 that is getting removed in form of CHI3, and the other side is your acid. But sir, you are again not reporting acid again, because medium is basic. So I should rather write RCOO minus and Na plus, because I am specifically using sodium salt. Now technically speaking, if you know this much, it is more than sufficient, but I'm just telling you the mechanism, because this mechanism will also help us in getting the basic idea of the next set of reactions that aldehyde and ketones used to give. So let us look at the mechanism also. Although this mechanism is not there in NCERT, but this essence will be used for further reactions. So why leave it? Let us see through it also. So ultimately what happens is, the carbon, the sp3 hybridized carbon next to a carbonyl group is acidic. This is acidic nature of the alpha carbon next to a carbonyl group. Although it is an acid, but it is not an acid who will just come and give H+. No. this hydrogen can act as an acid but in presence of a strong base. So who is acting as a strong base? So this is a strong base. And also through inorganic we know that X2 plus NaOH forms X plus and OX minus. So OX minus is also a strong base, the hypohalite ion. And if you do not know that inorganic, then just know this, that OH minus ion is also a strong base. So in presence of a strong base, even a carbonyl, even an aldehyde or ketone can also act as an acid. But what atom of an aldehyde and ketone? You should have a carbonyl group. You should have a next carbon as alpha carbon, which is it should be sp3 hybridized, and it should have hydrogen. So this hydrogen acts as an acid but in presence of a base. Like I've shown you that base comes and give electron to this hydrogen, and this hydrogen gives away the electron to this carbon, forming this carbon ion. Now this carbon ion is what? This carbon ion is stable. Why? Because of resonance stabilization. Oxygen is more than happy to take this electron. So this is a resonance stabilized carbon ion. Now, out of these two resonating structures, you tell me which will be a better electron donor. Sir, O minus is very stable. So rather carbon minus will give electron. Give electron to whom? Because X2 has broken as X plus and X minus, so now X plus will attack. X plus will attack where? It will go to this minus and this intermediate is formed. But you will say, sir, now this alpha carbon still has 2 hydrogen. So do this again. Do what? Remove hydrogen, add X plus. Remove hydrogen as H plus, add X plus. So ultimately you can get CX3. Now, because medium is basic, because of the minus I of the halogens as well, the positivity on this carbon is much increased. So even this OH minus will now have a capacity to do nucleophilic addition. Rather not addition, because this will get substituted. So nucleophilic substitution. So this OH will be going over here, sir, but you have not written OH. Why written O minus? Because again medium is basic. So OH will be formed and it will give H plus to the medium and will form the corresponding salt of carboxylic acid. And H plus, this CXC carbon with 3 halogen will take H plus of the acid given and will form CHX3, and this will get precipitated. So now because we know, so who all can give haloform test? Sir, all methyl ketones. What if you do not have a methyl ketone? So a very important point over here, let me write it for you because many students miss that point. So who else can give haloform test? Obviously methyl ketones, but one more structure can give positive haloform test. Which one? Sir, if I have a methyl group over here, ultimately this bond is getting broken. That means it is a strong oxidizing agent. Who is a strong oxidizing agent? Haloform. So rather, if I do not have a carbonyl group, let's say I have an alcohol. Now whatever R it may be. So if somebody can oxidize, somebody can break this C bond. See, that means if somebody can oxidize a ketone, can't you think that it can oxidize alcohol also? So this alcohol be first be oxidized. This H will be turned in, replaced into an OH. So after dehydration, I'll get a carbonyl group over here. So now it will become an methyl ketone again. So even such alcohols which have methyl group, so such alcohols can also give positive haloform test. A very famous point you should keep in mind moving forward. Now because we know these alpha hydrogens are acidic, so let us see the reactions. The first reaction being self-aldol. For example, I have this acetaldehyde, and now I know that if I furnish any base, then on the demand of a base can be NaOH, can be sodium carbonate, can be barium hydroxide, or any basic substance is present, maybe dilute, but if OH minus ion is present, then it can furnish electron to the alpha hydrogen, thereby creating a carbanion, and that carbanion is resonance stabilized, so it can easily be formed. I hope we already know this thing. Now, because this nucleophile is stable, so it can do a nucleophilic addition. So this is again, after knowing this is again the first set of reaction, which is nucleophilic addition for us. So if I just do nucleophilic addition, then I should add this nucleophile to whom? I should add this nucleophile to another. That's why the name is self-aldol, because if you have, let's say, 1 gram of acetaldehyde, it will be having crore and moles of molecules. So 1 molecule of acetaldehyde has formed this nucleophile, and it can attack itself. That means it can attack the another molecule of carbonyl compound, that is the acetaldehyde itself, because that carbon is again having delta positivity. So this minus can easily attack over here, which will result into the movement of that double bond O as O minus. Now the H plus that has been furnished to the solvent will be given to this O minus. So let us directly try and understand how to make the product in a single line. So what you should do is that we have thought of this alkyl, this aldehyde as a nucleophile. So let us make that aldehyde. This aldehyde is having CH and a double bonded oxygen. This CH3 has just turned into CH2, which is acting as a nucleophile now, and this nucleophile has just been introduced to another carbonyl carbon. The carbonyl carbon is CH. It was initially having double bond O, but now it will turn into O minus. It will take H plus from the solvent, and what alkyl group it is having? It is having one methyl group. Now this is generally the functional group. The next carbon, the carbon next to functional group, I hope we know, it's called the alpha carbon generally. So it is the beta carbon. So at this stage, what you get is a beta hydroxy carbonyl compound. It can be aldehyde, it can be ketone, because I have taken an aldehyde over here, so it will be a beta hydroxy carbonyl compound. Now whenever such compounds are formed, if you just supply a minimum amount of heat, then what rather happens is dehydration. That too, dehydration produces what? Alkene. But because this is a this is a double bonded carbon, so pi sigma pi, so a conjugated alkene will be rather very stable. So you take OH of the beta carbon and you just take H of the alpha carbon. So this will rather undergo dehydration and result in the formation of, this is an aldehyde, the first carbon. Post that I have now a CH, because one hydrogen has been removed, double bonded with the another set of the same alkyl halide, that is sorry, not alkyl halide, I mean carbonyl compound. So this is CH bond CH3. Now let us name this compound. This is carbon number 1, 2, 3, 4. So this is nothing but bute 2-ene, and at first carbon you have an aldehyde, so vowel get strike down. So this is known as self-aldol condensation. Now I hope you know how to quickly make this product. So if you know how to quickly make this, let us apply that and learn cross aldol. Now what is cross aldol? Suppose now I have mixture of two aldehydes, and both these aldehydes are having the sp3 hybridized alpha carbon, which is having an hydrogen. So in presence of base, both will be able to produce a nucleophile. But now what will be the products? Are now self will also be formed, cross will also be formed. So the first important thing is, although it is not asked in JEE, I mean the number of products are asked, but this has not been asked, but it is a very probable question asked many times in advance. So obviously how many products will be formed? Sir, 4. One will be when this nucleophile attacks itself, then when this nucleophile attacks itself, so one will be self and one will be cross. So let us make the 4 products and make them in the order of the percentage they are formed. So out of those four products, what will be the major product? So for that, you should always understand and have this feeling that cross product is generally more more formed. Why? Because if you have 100 molecules of this, then 100 molecules of this, and what then the probability of this having reaction with the other is obviously large. Therefore generally cross product is more than self product. So let us first write this conclusion that generally cross product is more in magnitude than self. This is point number one. Now point number two, we definitely know that aldehyde and ketone who has a higher ability to have nucleophilic addition, sir, aldehyde. So rather combine these two things, sir, make a nucleophile of ketone. Why? Because cross product is always the major product. So when who is ketone over here, sir, this Q. So when this Q minus as a nucleophile will attack whom? Aldehyde, because cross is the major product and reactivity, nucleophilic addition of aldehyde is more. So when Q minus will react with P, it will form the product number 1, which will be your major product. So I'm writing the product in the order of percentage yield they are produced. I hope we are clear with this. So let us make its nucleophile directly. So this CH3, this carbonyl group, one CH3 will become CH2 and will act as a nucleophile. Now this nucleophile will attack whom? So let me make with a different color. This minus will attack to the carbonyl group. Carbonyl group of what? Of aldehyde. That too cross product. So aldehyde of this, that means this CH, which was having a double bond O, will become O minus, will take H from the solvent, and what alkyl group it is having? Just this CH3. Now post that, we know this is carbonyl group, so this is alpha carbon, this is beta carbon. So after dehydration, what rather we should get is 1 2 3. So 1 2 3. The second carbon is having a double bonded oxygen. Third and fourth carbon will now have a double bond, and it is still connected with a methyl group. I'm not unnecessarily writing hydrogens so that you can know how to make the product quickly. So let us name the product. This is 1 2 3 4 5. So your product will be, I'm not writing the name, I hope we are clear with this, but this is pent 3-ene 2-one. So this will be the most product produced in the maximum percentage, so most major product. Now what will be the second dominating product as per percentage yield, sir? We definitely know cross product is more, but we also know that aldehyde are not they are very reactive towards nucleophilic addition. So what will be the other cross product where nucleophile of this will attack this carbonyl group, but it is a ketone, and we know ketone has very less nucleophilic addition reactivity. So rather I would give more preference to attack on aldehyde. So now I will give preference of having a nucleophile on aldehyde, whether it is self aldol. So now at second stage, considering that condition, that aldehyde has a higher reactivity towards nucleophilic addition, therefore I am saying now I am not thinking of cross product, I am thinking of aldehyde first. So when P minus will attack P, although it will be a self product, but because aldehyde is receiving a nucleophile, so it would rather be a more percentage produced product, produced product at the second position. First is that one is the most the major product, the product produced in the maximum percentage, so product number 1. So major product number 2 will be this one. So let us directly draw it. I hope we have already drawn it. So let me draw it quickly. So this is aldehyde, the CH2, this CH3 becomes CH2. I just do not write this H. So this CH3 becomes the nucleophile. It will attack the carbonyl carbon, this carbonyl carbon will become OH and it is further connected with a CH3. Why I'm doing this? Because this OH will be gone, this H will be gone, and rather you will be introduced with a double bond. So name will be 1, 2, 3, 4. Now obviously we have already formed this product, so I hope we are clear with this also. So this is our product number 2. Now what is the product number 3? So product number 3 will be again cross product. So what cross product we are left with? Sir, Q minus has attacked. Now let us use P minus as a nucleophile and attack this Q, although it is a ketone, but we do not have any other option. So when P minus will attack the Q product, so it will be also a cross product, but because ketone is receiving, so I am giving it number 3. Now what is P minus? Sir, P is this, so this minus, so that means I have CH double bond O. This CH2 is just getting added to this carbonyl carbon. So this carbonyl carbon will become OH, a CH3 over here and a CH3 over here, because that was a ketone, so it will have 2 methyl groups. Now again, dehydration, so this is alpha, this is beta, because this is carbonyl group, so OH and H. I hope we are clear and we can form the product with at least good amount of speed if we are having good practice. So CH double bond C and 2 methyl groups. Let us name this compound. This is 1, 2, 3, 4. So third carbon is having a methyl, so it becomes 3-methyl bute, 2-ene, 1-ul. Now the fourth product and the product produced in the least percentage of amount will be the when Q minus attacks Q. So it is a self product, and self product when ketone is having the nucleophilic addition. So CH3 C double bond O, this CH3 has just turned into CH2 and it is attacking ketone only. So the C double bonded O will become OH, a CH3 over there, a CH3 over here. Now let us see those alpha beta carbon carbonyl groups. So this is alpha, this is beta, OHH. So post dehydration, I'm having CH3, C double bond O, CH, double bond C, CH3 and CH3. Let us number this also. This is 1, 2, 3, 4, 5. Now it is also having a methyl, so this is 4-methyl pent 3-ene and 2-one. That's an aldehyde, that's a ketone. So actually cross product has produced 4 products, and we have even categorized those 4 products on the basis of percentage yield as 1, 2, 3, 4. I hope we are clear with this. Now it was the third type of aldol was actually not there in NCERT. It was loved by advanced, but now mains have also started asking a lot. For example, you have 2 carbonyl group in the same compound. For example, I have 6-oxoheptanol, hept as in 7 carbon chain. So this is, let's say, 1, 2, 3, 4, 5, 6 and 7. I'm writing it like this so that you can understand that why cyclization is taking place. So although this is a straight chain carbon, but I'm deliberately writing. You should also have a practice of writing like this. Now this is first carbon, so 6. So okay, let me number it also for your simplicity. This is 1, 2, 3, 4, 5, 6 and 7. Sixth carbon is having oxo, so that means a double bonded O, ketone. And first carbon is having ul, that means it is an aldehyde. Now we definitely know who has a greater reactivity of receiving the nucleophile, aldehyde. So you tell me this carbon will receive nucleophile or that carbon. So obviously it is quite clear to us that this is aldehydes, so rather this will try to get the nucleophile. Now where is the nucleophile? The other carbonyl group. So either this carbon can form a nucleophile, this carbon also can form a nucleophile. If this carbon forms a nucleophile and attacks this carbon, then how many carbon chain you will, then what membered carbon chain we'll get? Sir, 1, 2, 3, 4, 5, 6 and 7. Actually, we know, if you do not know, I'm telling you, 6-membered ring is best. After that, try to make a 5-membered ring. And if not possible, then make a 7-membered ring. So rather, if we try to do that by removing hydrogen of this carbon, then I'll get 1, 2, sorry, I'll be attacking this. So 1, 2, 3, 4, 5. I will be getting a 5-membered ring. So instead of this carbon, I'm thinking of using a base on this hydrogen, and minus will be formed over here, and when this minus will try to attack this carbonyl group, this O double bond O becomes OH. I hope we can now at least try to make the product. So let us try to do it. So this is a carbon. The double bonded O has just turned into an OH with this carbon, with this carbon, with this carbon. Now this carbon has been just now introduced with this carbon, although it is still having this C double bonded O and CH3. Now, I hope it is quite clear to us that this is not a 5-member structure that we like, but still at least do the, because this is carbonyl group, so this becomes alpha carbon, this becomes beta carbon, so beta will give OH, alpha will give H, and post dehydration you can easily form the compound. What compound? I know it is a 5-membered ring, so let us draw a 5-membered ring. Now this 5-membered ring has a double bond over here, so let us make a double bond over here. The carbon having double bond is further connected with COCH3. The carbon having double bond is further connected with COCH3. So I hope we have formed the product, and that product is your major product, which is definitely a ketone, but a alpha beta unsaturated ketone. So this finishes our Aldol condensation, and going to the last set of reactions shown by aldehydes and ketones, and they are other reactions. Now why we have came down to this other reactions? Because ultimately we now know that aldehydes can act as acid also, so they react in presence of base. But what if you take aldehydes and you take those bases again? But if those aldehydes do not contain any acidic alpha hydrogen, then whether they will not react with base? No, they will react. How they react has been patented by a scientist, and a naming reaction has been known in NCERT with detailed mechanism. A very important and a repeated question is asked from this section, which is Kenny-Zaro reaction, which is shown by those carbonyl compounds which are not having acidic alpha hydrogen, like formaldehyde. Can you think of the structure of formaldehyde, sir? Obviously we can. What is it? Sir, this is H, C double bond O and an H. Sir, it is not in fact having any alpha carbon only. So rather what happens is, under the presence of a base, it goes disproportionation. What is disproportionation? The same compound gets oxidized also, so it forms HCOOH. Why I am not writing H? Because acid in presence of base forms a salt, so rather I should report sodium salt of corresponding carboxylic acid, and this very compound will undergo reduction also. So one carbon alcohol is called methyl alcohol. So this disproportionation product will be your answer. Similarly, if I have benzaldehyde, then benzoic acid, rather salt of benzoic acid, and then benzylic alcohol. So oxidation also, reduction also. Over here, although this is having an sp3 hybridized carbon, but this carbon is not having any hydrogen, it is having just 3 methyl groups, so it also cannot act as aldol condensation. So rather what this will also do, Kenny-Zaro, that means oxidized also. So Me3 carbon, the COONA, and it will go reduction also, that is Me3C, and this carbonyl carbon will get again H and OH. So oxidized also, reduced also. Sir, how it is happening and why it is required? For good questions it is required. In fact, these days in January attempt only, even the mechanism was asked in theory. So what is the mechanism? I hope it is quite easy also to understand now, because we know we have a minus, and carbonyl carbon definitely loves having nucleophilic addition. So nucleophilic addition will take place. The moment this minus is transferred to this carbon, actually this becomes the rate determining step, where hydrogen is removed in form of H minus, and this hydride now act as a nucleophile for the another carbonyl compound. I mean of the same carbonyl compound. So this H minus acts as a nucleophile and attack as a nucleophile to the another same carbonyl compound, which is formaldehyde in our case in this example. So this CH2 when receive this H minus, this O will form O minus. So this starts looking like an alcohol, this starts looking like an acid, but sir, we know carboxylic acid is a strong acid, so rather now proton transfer will take place. So this will release H plus, this will take that proton and will form the corresponding alcohol, and this will form the corresponding salt of carboxylic acid. So how is it helping you to understand? Sir, that means those carbonyl compound which can have more tendency towards nucleophilic addition, that carbonyl compound will become carboxylic acid. Sir, why you are telling us this? This is an advanced topic. Why did this mechanism is not there? No. Mains have started asking it because advanced loves it. Now, for example, if we have such question, although this is a topic of advance which is intramolecular kinase, but now after knowing that basic of mechanism, it is quite easy for us. Like for example, we have two center of carbonyl carbon. Now, which carbonyl carbon should we start attacking? This OS O minus will go to what? Aldehyde or ketone? Sir, it will go to aldehyde, and where OH minus will attack, that carbon will turn into an acid and will force the other carbonyl group to get reduced. So ultimately, I hope it is quite easy and evident for you after knowing mechanism that because it is a ketone, so it will get reduced. So this becomes CH and the double bond will also become, so this has to receive hydrogen, that means this has to get reduced, forcing the aldehyde carbon to oxidize. So this is double bond O will again get O minus, and with that Na plus it will form a salt. So I hope you can mark the product of this intramolecular kinase reaction. Moving forward, moving to the electrophilic aromatic substitution reaction shown by this minus R applying carbonyl group, but because these carbonyl groups are very polar, therefore they also react with Lewis acid. Therefore, I mean, this is God's grace as well that at least they show very less number of SE reactions, where only nitration and sulfonation are shown by them, and because they are minus R, so they are meta directing group. So the electrophile NO2 plus and the electrophile of the sulfonic acid group get substituted at the meta position, and you get a meta substituted product. All those SE reactions which uses Lewis acid reacts with the carbonyl group, and as a result of which they do not have that the traditional SE reactions. So with carbonyl group and their derivatives, only nitration and sulfonation is observed. So this finishes our chapter of carbonyl compounds, that means of aldehydes and ketones, but carbonyl group is also present in carboxylic acid, and these carboxylic acids we have almost already done. But to consolidate it, let us list all those preparations and reactions of carboxylic acid. So starting with the preparation of carboxylic acid, which we have already seen. So the first method of preparation of carboxylic acid is just the oxidation reactions. So remember, in chapter of alcohols in aldehydes and ketones, we have seen that alcohol, 1 degree alcohol subjected to strong oxidizing agent produces acid. 2 degree alcohol subjected to strong oxidizing agent produces ketone, but ketone on vigorous oxidation can produce again acid. The Popov's rule we have already done. Similarly, aldehyde when treated with strong oxidizing agent produces acid. Ketones are difficult to oxidize, but now we know that under vigorous condition using Popov's rule, ketones can also be further forced to undergo oxidation and produce the corresponding acid that we have already seen. Now, the alkenes, we know you can use strong oxidizing agent, and you can also do oxidative ozonolysis. So that can also break the olefins and create a double bond O, and all the H replaced by OH will also create the corresponding carboxylic acid. So these oxidation reaction, guys, we have already seen. So see, at least one reaction we already know, we have already studied, we are just summarizing everything now. Next is while the oxidation of aromatic aldehydes we have seen, I have told you over there also, NCRT listed over here. But for alkyl benzenes, only the benzylic carbon undergoes oxidation. Obviously, it undergoes oxidation using a strong oxidizing agent, and generally, if you use a strong oxidizing agent in acidic medium, you can form the corresponding carboxylic acid, but only on the benzylic carbon, because that benzylic carbon is reactive. But industrially, it is observed that if you use KMnO4 in a drastic condition, now what becomes a drastic condition for KMnO4, which makes it even a strong oxidizing agent? Ultimately, you use KMnO4 in a basic medium and then you heat. So ultimately you get the corresponding carboxylic acid, but because medium is basic, so what product you should report? The corresponding salt of carboxylic acid. And how to report acid? So post acidification you can only report the corresponding benzoic acid. But again, I'm mentioning you, in the reactions of aldehydes, you have seen that with ITAD reaction and with chromium complexes, the carbon that is at the terminal position used to undergo oxidation. But over here, this is specific reaction of this benzylic carbon. Sir, if the degree of this benzylic carbon increases, then no matter. Even if this benzylic carbon is some more degree, or even it is a double bonded carbon, in all the cases this benzylic carbon can undergo oxidation once you use this strong oxidizing agent and you get the corresponding carboxylic acid. Yes, but definitely one thing, yes, obviously instead of having double bond over here, it would rather be more comfortable if we make a double bond over here, which will make this carbon at least having one H. Although I have not written it because it is a good question logic, but if this benzylic carbon is a 3 degree, I mean it is having no C bond H, then in that case its oxidation even using KMnO4 in basic medium and heating will not take place, because again it is an experimental fact that if you have a carbon which is not having any C bond H, then that benzylic carbon is not supposed to get oxidized. But I have not listed it over here because whatever question we find in mains, you just have to understand this, that whatever benzylic carbon you have, you make oxidation of that carbon and you give the corresponding carboxylic acid. Moving forward, now the preparation of carboxylic acid, the third method of preparation is nothing but hydrolysis of acid derivatives. And we know how many acid derivatives we have? 4. So all those acid derivatives, when they are subjected to hydrolysis, they reproduce their parent carboxylic acid. So starting with the first acid derivative, the ester. Now I'm not doing it with all the acid derivatives, but you should understand this. Sir, understand what? That hydrolysis can take place in any medium. Any medium will create their parent carboxylic acid. But obviously, if the medium is acidic, then you report the corresponding carboxylic acid only, because it's an ester. So this part will form an alcohol. But if the medium is basic, sir, we know that carboxylic acid has stronger acid than water. So rather they react with base and form salt. So what product you should report if the medium is basic? Salt of corresponding carboxylic acid. If the question is asking you to do acidification, then post acidification you can definitely report the corresponding carboxylic acid. But in basic medium, what you should remember, you should report the salt of corresponding carboxylic acid. Similarly, if I have acid anhydride, then again post hydrolysis you produce because acid anhydride is produced by both carboxylic acids. So like you have benzoic acid, ethanoic anhydride, so you get corresponding 2 carboxylic acids. If you have acid halide, which is the famous acid halide, acid chloride, so this undergoes hydrolysis, forms the corresponding carboxylic acid and HCl. Again, if medium is basic, you should report the salt, and post acidification you should get your acid. The last acid derivative. Now in the formation of cyanohydrin, I've told you. Now this is the time to list it. Even nitrile. Now nitrile is not a derivative of carboxylic acid, but if nitrile is also subjected to hydrolysis in whatever medium, acidic medium, basic medium, initially it forms benzamide. Now amide is a derivative of carboxylic acid. So ultimately nitrile forms amide under mild condition. Now what are these mild condition? If no heat is mentioned, that is a mild condition, or sometimes even option will tell you. But if you do the same hydrolysis under heat, then this makes the condition strong, and under strong condition this amide also undergoes hydrolysis, releasing ammonia gas and forming the corresponding carboxylic acid. Again, if medium is basic, what product you should report? Corresponding salt of carboxylic acid, and post acidification you should report carboxylic acid. I have repeated this many times. Make sure that your eyes are open while solving questions, because you will find so many questions applying the same logic. Now the last method of preparation of producing carboxylic acid is, again, we have done that. So if you use Grignard reagent, we know this is a nucleophile. It will attack the positivity. So the carbonyl carbon which I'm using over here is the carbon of CO2, because the CO2 is also highly delta positive, because this carbon is in +4 oxidation state. So whatever alkyl or aryl group you're having, it will act as a nucleophile in presence of dry ether, and intermediate will be formed, and post hydrolysis you will again get your corresponding carboxylic acid. And this method is also a beautiful step, that if you want to create a carboxylic acid with one carbon atom more, so obviously you can see that this CO2 carbon is getting added to the parent chain that is being given by the Grignard reagent. So this also helps in conversions of some important questions. So moving to the chemical properties. Now, like alcohols, the carboxylic acid will have different set of chemical properties, and again, like alcohols, the first set of reactions will be those reactions in which O bond H of carboxylic acid will break. Obviously, if O bond H is breaking, then carboxylic acid will act as an acid. So this acid can react with metal also, can react with base also, because carboxylic acid are stronger acid than water, and they can even react with carbonate salts, because carboxylic acid is even stronger acid than H2CO3, forming hydrogen gas, neutralization as in water, and carbonic acid is unstable, so it will decompose and form CO2 and H2O, creating brisk effervescence. Now again, in the chapter of alcohols also we have done, and in the in GOC also we have done lot of acidic nature comparisons, applying the resonance, effective, inductive and hyperconjugation effect. So summarizing everything over here, if I have electron withdrawing group, then this electron withdrawing group is going to stabilize this conjugate base, which is carboxylate ion. So equilibrium will be shifting in forward direction. That means acidic nature will be increasing. So electron withdrawing group increases acidic nature, and talking about the opposite behavior, if you have electron donating group, then this carbon ion will get destabilized, and therefore acidic nature will reduce, because equilibrium will be shifted to backward direction. A strong acid will have a larger value of Ka and a smaller value of pKa. The most electron withdrawing group is that group which is applying -R. After that, minus hyperconjugation. After that, -I. So all those logics of inductive effect will definitely again be applied over here, but because we have sufficiently discussed separately in GOC and in mains level of question, only this much knowledge is more than sufficient. So I am giving you a trend, an acidic nature comparison directly from NCERT, which directly employs the logic of electron withdrawing group increases acidic nature and donating group decreases acidic nature. Obviously we should know that CF3, sir, 3,3 fluorine, that means it is strong -I, so it is strongest acid. Not among every acid, among the given acids. Obviously, if that F3 is replaced by Cl3, then acidic nature, then -I will decrease. So that will be strongest, this will be weakest with respect to that one. And if chlorine is also getting reduced, then obviously this is much weaker. But ultimately, I have two chlorines. So having two minus I group is better than having one minus I group. One minus I group will have less in electron withdrawing nature. So this is also helping us to ultimately have a feeling that 2 chlorine minus I is stronger than 1 NO2. Obviously minus I of NO2 is larger than nitrile, therefore nitrile is a weaker acid. CN is a weak minus I group than NO2. Then fluorine is a weak minus I group than CN, therefore it is also much less. Obviously you can see the other products, but one important observation you should make note. This is formic acid. Now formic acid is having hydrogen which is applying nothing, but formic acid is a stronger acid than benzoic acid. Sir, but C6H5 applies minus I. Yes, ultimately benzene ring apply minus I, but if you compare this minus I with respect to hydrogen, this benzene ring is also applying plus R to the carboxylic acid group. So although it is minus I, this is good, but because of its plus R, this benzoic acid is weaker acid than simple formic acid. But I'm not denying to the fact that the phenyl group does not have a minus I. It has a minus I, and because it has a minus I, therefore this benzoic acid is a strong acid than any of the aliphatic acid, except one aliphatic acid, which is formic acid. Why? Because apart from the minus I, it is also having a plus R nature, which reduces its acidic nature with respect to formic acid, but only with respect to formic acid. So that is even an NCRT logic, because this data has been given on the basis of the value of Ka, which are experimentally determined. So make note of this, that ultimately you know this trend. Although for acidic nature comparison, there are various other factors like steric inhibition to resonance, ortho effect, but those are all specific for advanced. So if you just go by this NCRT logic, your mains question and even some of your advanced question will be more than sufficient. But obviously some spices has to be added for advance, but which I am deliberately skipping because we have already extended a lot of time, and I want this one shot to be precise for you for your April mains attempt. So moving to the next slide, talking about the chemical properties, the second set of chemical properties where you have cleavage of C bond O, like alcohols. Carboxylic acid can also break their C bond OH. Ultimately, whenever carboxylic acid will break their C bond OH, the OH will be substituted, and sir, whenever OH gets substituted, we form the corresponding acid derivatives. So ultimately we will be seeing 4 type of reactions over here, and these reactions will be producing what? They will be producing corresponding acid derivatives. So you can either take that reactions involving cleavage of C bond OH is a reaction of carboxylic acid. It is also preparation of acid derivatives. Now how this acid derivatives are produced? The first one, you just take carboxylic acid and force it to undergo dehydration by using dehydrating agent like strong acid and heat, like P2O5 and heat. It will ultimately undergo dehydration. The Dabba method will be helping you. The HOH gone, and you will form your corresponding acid anhydride. Now if this carboxylic acid, being an acid, reacts with ammonia, a base, obviously you form a salt. Ultimately you should report a salt only. When this salt is further subjected to heat, then it undergoes dehydration and forms corresponding amide. So 2 acid derivatives done. Now if I have this carboxylic acid, now ester and acid halide. Ester we have separately done with mechanism in the chapter of alcohol, so I'm not going to repeat, but yes, logic I'm giving you. Carboxylic acid gives OH, and alcohol, any alcohol, aliphatic alcohol or aromatic alcohol, gives it hydrogen. The reaction takes place in acidic medium and you get corresponding ester. The method is known as esterification. And what about acid halides? So if you use any of this, phosphorus trichloride, phosphorus pentachloride, or SOCl2, the reagents we have even seen with alcohols, you form corresponding acid chloride, but byproducts are also important. So with PCl3 you get phosphorus acid, With PCl5 you get POCl3, which is phosphorus oxyacid, phosphorus oxychloride and HCl, and with SOCl2 you get sulfur dioxide and HCl. So moving forward, moving to the third set of reactions, which involves the complete COOH group. So if you have complete COOH group participating in a reaction, then the first type of reaction is the reduction. We have already seen this reaction. Carboxylic acids can be reduced using strong oxidizing agents like lithium aluminum hydride or diborane, followed by hydrolysis, and they will result into the formation of obviously 1 degree alcohol. But because this lithium aluminum hydride is although very strong reducing agent but very expensive, so creating alcohol will not be economically possible. So we have seen this in the chapter of alcohols, that an rather economical, a cheaper way to convert it into an acid into an alcohol is first convert into an ester. Use an alcohol in acidic medium, it will give rise to the formation of an ester. Now this ester can be easily reduced using a cheaper reducing agent like catalytic hydrogenation, resulting into the formation of this same alcohol. And whatever alcohol you have used in order to esterify the corresponding acid, it is again regenerated. So industrially it is quite economical. But if we talk about diborane, then diborane is a reducing agent which can only reduce carboxylic acid. Like lithium aluminum hydride, diborane is not that strong reducing agent because it can only reduce this parent carboxylic acid. Generally it never reduces the acid derivatives. So it can't, although lithium aluminum hydride can even reduce acid derivatives to form corresponding 1 degree alcohol. Moving to the second and third set of reactions, which we have already seen in the chapter of hydrocarbon, but although I'm not discussing the complete mechanism, that we have already done in hydrocarbons chapter, but for the mains level of questions, this much is more than sufficient. Like the first set of reaction where complete COOH group participates, I mean after reduction, the two set of reactions which results into the formation of alkane. First is soda lime decarboxylation. For that you use sodium or potassium salt of carboxylic acid. You react it with soda in presence of lime. It will result into the formation of release of CO2 in the form of Na2CO3, and you produce an alkane, but this alkane will have one carbon atom less than the parent carboxylic acid. Similarly, if you take the similar salt of sodium or potassium salt of carboxylic acid, but if you put that salt in water and pass electricity, that means you are going to do electrolysis. So this becomes coal-based electrolytic method, where at anode you generate an alkane, but a higher alkane containing what number of carbon atom? Ultimately this CO2 is going to be released. This CO2 is released at anode only, but post release of the CO2 you get a carbon radical. So this radical gets chain termination with another radical of the same kind, and that's how you get a higher alkane. And in soda lime decarboxylation, the ratio of soda is to lime is 3:1, and function of lime is not to react, because lime is because NaOH is highly hygroscopic, so we want NaOH to react with this organic compound, do not with any other thing. So even if there is moisture present, then the moisture can react with NaOH and NaOH will not react with this carboxylic acid. So to keep the reaction mixture dry, we use calcium oxide. Now these are some reactions, and with proper mechanism, we have discussed this in the chapter of hydrocarbon. But if you go just by this, then such questions is very probable for you, and these questions are actually valid for JEE mains. For example, you have propanoic acid. Now we know acid reacts with even metal, even with base, even with sodium carbonates, and they will form the corresponding salt of carboxylic acid. So you have produced a 3 carbon carboxylic acid salt But if you do electrolysis, then CO2 will be released, but you form a higher alkane. Higher alkane having these two carbon, because this carbon has been gone in the form of CO2. So what alkane you get? You get a higher alkane but a butane. And if you use soda lime decarboxylation, then only this alkyl group will be remaining, and this will be getting hydrogen, and you will rather produce a smaller alkane, which is ethane. So if you just know that basic reaction without the actual mechanism, but the actual mechanism you should know for good questions, which we have separately discussed in the chapter of hydrocarbons. Moving to the last set of reactions finally. So those reactions where you have the you have some substitution, not in the carboxylic acid remains as it is, but in the substituted portion. There are two famous reactions, the first one being the HVZ reaction, Hell-Volhard-Zelinsky reaction. It is a very important naming reaction. That's why I've even used the data from NCERT only, because this itself without any mechanism is more than sufficient. What you should know: the reagent, you use red phosphorus in presence of any halogen. The halogen is most commonly Br2 and Cl2. You can either use phosphorus trihalides as in PCl3 or PBr3 followed by hydrolysis. What happens is, whatever the number of alpha carbons you have. What is an alpha carbon? Carboxylic acid is the functional group, so the carbon next to functional group is your alpha carbon. The number of hydrogens you have, those hydrogens can be substituted by what? By the halogen. So if you do it one time, you will get a mono substituted product at the alpha position. So this is nothing but alpha halo carboxylic acid. But if you do this with excess of reagent, for example, you are doing bromination, and because I'm having two alpha hydrogens, so if I do excess of bromination, then both these hydrogen are substituted by bromine. And similarly, if we do chlorination but excessive chlorination, then both these chlorine are substituted by, both these hydrogens, the alpha hydrogens, are substituted by chlorine. A very famous reaction, a direct reactions are asked in your JEE mains. Moving to the last set of reaction is again the electrophilic aromatic substitutions, which we have already seen in carbonyl compounds. And like carbonyl compounds, because here also you have the carbonyl group which reacts with Lewis acid as in anhydrous AlCl3. So Friedel-Crafts reaction not seen, but obviously nitration, sulfonation and bromination is famous, where you get a meta substituted product, because this carbonyl group is electron withdrawing and a minus R group. Moving forward, now let us try this question from JEE Mains 2019. Now you are given, sir, this is an ester, this is alcohol or maybe toluene. Now the reactant is anhydrous AlCl3. So anhydrous AlCl3 will give us an idea that it is asking us about Friedel-Crafts reactions. Now sir, there is no alkyl chloride, so no alkylation, but yes, there is acyl chloride. So the lone pair of electrons on oxygen, sir, somebody will say this also has lone pair, but hybridization of that oxygen is what? Sir, because it is a double bonded oxygen, so it will have more S, it will have more S character, and because it will have more S character, so that means it will be electronegativity. And we obviously know that carbonyl, the acyl group should have, the carbonyl carbon should have a positivity. That means this will act as a base and will give electron to this Lewis acid, and definitely the bond will be opening like this and a positive charge will be coming on the carbonyl carbon. Now we have seen the electrophile. Now let us come to the structure. OH is a plus R group, CH3 is a plus hyperconjugation group. So who is more electron donating? Plus R. So at ortho and para, OH will create huge number of electron density, but because this is also a huge compound, so para will be more preferred and a para substitution will be taking place. So this carbon should be getting attached with this para position with respect to phenol. So let's say I have this phenol, and at its para position I'm making this bond. So let us number this. This is carbon number 1, 2, 3 and 4. That is oxygen. So with this carbon, which is actually a double bonded carbon, this is 1, this is second carbon, this is third carbon, and this is fourth carbon, and there is again one O. Now this oxygen has given electron to AlCl3, so this is minus and this is plus. Now because oxygen has given an electron, so it must be obviously this will be neutral. Okay, this will be neutral because oxygen has got the electron, so this will be OCl3. But ultimately this OCl3 has become a good leaving group. Moreover, we have supplied with temperature also. Now because of the supply of this temperature, this bond will be broken and a positivity will be coming over. That means I have an alkyl carbocation again. Now this CH3 is also electron donating and it will give electron at its ortho and para position. So its para position is this. So at its para position, this minus will be getting attached with this carbon. So how many carbon chain, what is the number of ring structure that I've got? This is 1, this is 2, this is 3, this is 4, this is 5th, and that will be the 6th carbon. So 6-membered ring is good enough. So let us see, OH should have carbonyl group. No, it is not a carbonyl group, so gone. OH having carbonyl group at para position, it is not a carbonyl group, so gone. OH should have a carbonyl group. No carbonyl group gone. So if you just see the carbonyl group positioning, then only you know this is your answer, because OH, the para position, so there's a carbonyl group. This is carbon number 1, 2, 3 and 4. Fourth getting substituted at para position with respect to CH3, although you do not know it. What point I am making by solving this question, if you visually see this question, such questions will appear very difficult to you, but once you start solving it, you will get to know the theory also and obviously the question also. So what I've done for you guys is, I have given you such questions, whatever theory we have read, the similar logic will be applied, and these 13-14 questions I am now giving you as an homework. If you are listening to this one shot, take out your rough copy, and these all are very probable questions with whatever theory we have just read. So what you have to do is, take out your pen and copy, practice these questions along with the questions that we have given you in the practice sheet if you have time. But if you have boards, then after boards you should obviously do that, because practice and practicing the exact PYQs, because solving PYQ is the only holy grail to crack JEE, because that will tell you where you are missing the theory and you should revise that particular theory, not every theory. So with these words, I wish you very best of luck for your boards also and for your coming examinations also. And this is me, Gaurav Singh Arora, signing off. We'll see you in the next lecture.